Welcome to Math with Professor V. In this video, I'm going to be solving 100 questions, all having to do with sequences and series. And I'm going to start at the beginning of the unit, just with sequences, and then work my way through problems involving series, different tests for convergence, divergence, power series, Taylor series, Maclaurin series, you name it, I'm probably going to solve a problem on it. So you can use this as a comprehensive review for the unit, for some fun. I don't know why you're watching, but I'm here to help you. If you need a little bit more of an in-depth lecture on any of the topics that we're going to cover while solving these problems, then check out the description because I have videos linked that give you a little bit more background. But I'm just going to start working through all of these problems. So I hope you're comfortable, get a snack or a drink, and let's do this. So question 1 says, write the first 4 elements of the sequence. Notice we're starting with just sequences. So right here, this represents the general term of our sequence. Usually we use a sub n to represent the general term of a sequence. So that's natural log n plus 1 over n cubed. Now, what exactly is a sequence, right? It's an ordered list of terms. Another definition you'll see is that it's a function whose domain is the set of natural numbers. So we're only substituting in natural numbers for n, nothing else. So where should we start? They want the first 4 elements. Do we start with n equals 0 or n equals 1? You know, it kind of depends. How do you define the natural numbers? And it is highly debatable whether or not 0 is part of there. But let's just start at 1, since most of the time we do. So a sub 1 is going to be natural log 1 plus 1 over 1 cubed. So that's just ln of 2 over 1. A sub 2 is going to be natural log, plugging 2 in now for n over there, 2 plus 1 over 2 cubed. So that's ln of 3 over 8. A sub 3 is going to be ln 3 plus 1 over 3 cubed. So that's going to be natural log of 4 over 27. And then a sub 4, natural log 4 plus 1 over 4 cubed, ln of 5 over 64. Okay, good. Usually though, when I'm writing out my final answer for a problem like this, I'm going to actually list all 4 terms separated by commas in order. So first natural log of 2, then natural log of 3 over 8, natural log of 4 over 27, and natural log of 5 over 64. All right, very good. How was that one? Not bad, right? Look at you. Okay, let's move on to another. Same idea. We have 1/3 raised to the n. So again, a sub n is 1/3 raised to the n. This is actually a geometric sequence. Hopefully you've heard about a geometric sequence before, like in algebra or pre-calc. Because the terms have a common ratio r, that's what makes them geometric. So here we go, a sub 1, that's going to be 1/3 to the first. A sub 2 is going to be 1/3 squared, so 1/9. A sub 3, 1/3 cubed, 1 over 27. And then a sub 4, 1/3 to the 4th, which is 1 over 81. And then again, I would list them out separated by commas. 1/3, 1/9, 1 over 27, 1 over 81. Good? Okay, we're warming up. Let's do one more. Here we have sine of n times pi. So a sub n equals sine of n times pi. All right, so a sub 1 is going to be sine of 1 pi. What's sine of pi? Imagine your unit circle. You're over there at 180, 0, right? A sub 2, that's going to be sine of 2 pi. Sine of 2 pi, also 0. A sub 3, sine of 3 pi. 0 again. Wow. A sub 4. Okay, probably you realize, you're like, wait a minute, Professor V, these are all zeros. And you are not wrong. So let's just list it out. 4 zeros, that's what you get. Fabulous. Okay, now all of these sequences have been defined explicitly. Sometimes we have recursive sequences. So what is a recursive sequence or a recursion formula? It's when the terms of a sequence are defined using the terms that precede it, one or more. So notice here, they give me the starting point. They tell me, hey, the first term of your sequence is 1, and then from there, you're on your own. So to get the second term, you would take the first term divided by 1 plus 2, and so on and so forth. So whatever term I'm trying to find, I take the term that came before and divide by n plus 2. They look worse than they are. They're really pretty fun. So first term is 1, and they want the first 5 terms. That makes sense. They gave me a freebie, right? They gave me the first one. If I want the second term, then I'm plugging in 1 for n. I hope that makes sense. If I plug in 1 for n, then I'm finding a sub 1 plus 1, right? Which is a sub 2. And that equals the term that came before, a sub 1, over 1 plus 2. Remind yourself, n is 1, n is 1, n is 1, n is 1. Okay, so that's why they have to give me the first term, so I know where to start. A sub 1 is just 1. So a sub 2 is going to be 1/3. Good. That's from plugging in n equals 1. Now if I plug in n equals 2, then I'm going to have a sub 2 plus 1, which is a sub 3. And a sub 3 is a sub n is 2, a sub 2 over 2 plus 2. Okay, well a sub 2, where's that? That's right here. This is a sub 2. So it's 1/3 divided by 4, which is 1/12. Good. You all right? This is a sub 3. Now let's move on. N equals 3. I'm going to get a sub 4. So a sub 3 plus 1, that's a sub 4. It equals a sub 3 over n plus 2. So 3 plus 2. So take the term that came before, 1/12, divided by 5. That's 1/60. That's a sub 4. And then we have to go up to the first 5 terms. So one more. N equals 4. A sub 4 plus 1 is a sub 5. And how is that defined? A sub 4 over 4 plus 2. So that's 1/60 divided by 6, which is 1/360. So that's a sub 5. So now I'm going to list out A1 through A5. They gave me the first one, 1, and then 1/3, 1/12, 1/60th, 1/360. There we go. Okay. I know, maybe if you've never seen that, it might be mildly traumatizing, but you're fine. Let's do one more recursive sequence. A sub 1 equals 1, a sub 2 equals 6, and then a sub n plus 2 equals a sub n plus 1 plus a sub n. So this time they gave me 2 to start off with, because notice they're defining a sub n plus 2 in terms of the sum of the 2 terms that precede it. Ah, okay, that's why they had to give me more to start with. So a sub 1 is 1, a sub 2 is 6. A sub 3 would be a sub 2 plus a sub 1. If I just simply plug in 1 for n, 1 plus 2, that would give me a sub 3. And that's going to equal the sum of a sub 1 plus 1, which is a sub 2 plus a sub 1. Very good. Well, that's not too hard. I'm just going to take 6 plus 1, so that's 7. Do you get the hang of the pattern? Can we just write out a sub 4 now would be a sub 3 plus a sub 2. So 7 plus 6, that's 13. A sub 5 would be A sub 4 plus A sub 3, so 13 plus 7. And then we're done. They only wanted the first 5. And they gave me 2, so that's nice. 1, 6, 7, 13, and 20. There we go. Okay, how are we doing? Now, we're going to kind of go the other way. So find a formula for the nth term of the sequence. So here's the sequence. We're going to assume it continues forever. We start at 5, the next term 7, 9, 11, 13. So we're going up by 2. Do you notice that? We're going up by 2. This is an arithmetic sequence. Hopefully you've studied that a little bit in pre-calc. And when you need the formula for an arithmetic sequence, you take the common difference. So that's the amount that each of the terms is changing by to get from one to the next. And an arithmetic sequence can be represented by a linear expression in terms of n. So n to the first. So 2 is going to be the coefficient on n. So a sub n is going to be 2n and then plus or minus something. So how do you figure out how much to plus or minus? Well, you go, hey, this term right here, 5, that's the first term. So that means a sub 1 is 5. Right now, if I plug in 1 for n, I wouldn't get 5. I'd get 2 times 1, which is 2. So how much am I off by? How can I get from 2 to 5? I would need to add 3. And then just check that that works for the other terms. So this is a sub 2. 2 times 2 is 4 plus 3, 7. Boom. Let's try 3. 2 times 3, 6 plus 3, 9. Look at us. We are fantastic. And this works anytime you have an arithmetic sequence. This one's arithmetic. So I have a video on arithmetic sequences in case you'd never heard them or you forgot from pre-calc because it's been a while. But yeah, if this guy had been 5, 10, 15, 20, notice this time it's going up by 5s, right? Then you go, oh, it's going to be 5n, a sub n. And then in this case, I don't have to add or subtract anything because this one's 5, 10, 15, like so. If I switched it up though, say I made it instead, ooh, this is going to be fun, 2, 7, 12, 17, etc. These are going up by 5, yes? If I plug in 1, 5 times 1, 5. How do I get to 2? This time I would have to subtract 3. And then just check if it works for the others. So 5 times 2 is 10 minus 3, 7. Boom. And this works so long as it's arithmetic. Okay, so you have to have a common difference between the terms. Helpful, right? Helpful. Okay, obviously there's so many kinds of sequences. They're not all arithmetic, so let's look at some more. Here we've got this funky one. 2, negative 2. 2, negative 2. What is going on? They're telling you, hey, it's just a bunch of 2's with alternating signs. So to make the terms of something alternate, you need to include either negative 1 to the n or negative 1 to the n minus 1 or negative 1 to the n plus 1. What this does is just change the sign of the terms without actually affecting the magnitude or what the term is. So notice here, if you have negative 1 to the n, all of the odd terms, so the first term, the third term, the fifth term, they'll be negative because you'll have negative 1 to some odd number. And then all of the even terms are going to be positive. These two guys do it the other way around. So they would make all of the odd terms positive because n plus 1 or n minus 1, if n is odd, is going to be an even number, right? So you just got to look and see which one's appropriate based on are the odd ones positive or the even ones positive. No big deal. And then what else is going on? You've got a 2 in every single term. So that's not changing. So you're just going to go, okay, a sub n is 2 times one of these guys, either this one or one of these. And these do the same thing. So they're interchangeable, okay? So this is the first term, third term, fifth term. So it looks like the odd ones are positive. Odd are positive. So I'm not going to want to pick this one because the odd ones are negative here. I'm going to pick either one of these. So 2 times negative 1 to the n plus 1 is appropriate. Or you could have a sub n is 2 times negative 1 to the n minus 1. And check. If n is 1, 1 plus 1, 2. Negative 1 squared is going to be positive. Boom. Then the next one would be negative, so on and so forth. Same thing here. Now, if instead it was negative 2, 2, negative 2, 2, like that, and you see how this time I made the first one negative, then you would go for a sub n is 2 times negative 1 to the n. Then you pick this guy. That way, the odd terms, the first, the third, the fifth, end up negative. That's the only difference, okay? So this one makes the odds negative. This one makes the evens negative. You could use either, okay? And then we don't use negative 1 to the, were you wondering, n plus 2? You're like, no, I wasn't wondering, Professor V, but thanks for bringing it up. Let me show you. Negative 1 to the n plus 2. Negative 1 to the n. Using my laws of exponents, I could write it as negative 1 to the n times negative 1 squared. That becomes just positive 1. So we have negative 1 to the n times 1. So we don't use negative 1 to the n plus 2 because it does the same thing as this guy. Okay? I think you got it. You're going to see so many alternating sequences and series throughout this unit, so it's time to really embrace this. Yes, we love it. Just say that to yourself. Okay, here's another one. 1, negative 1/4, 1/9, negative 1/16, 1/25. And then look at this. They're holding your hand. They feel so bad for you. Reciprocals of squares, with alternating signs. Yeah, we gathered as much that it was alternating. They want you to notice that we have perfect squares in the denominators. Yes, this is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. Exactly. So a sub n, notice every single term has a 1 in the numerator. And then you have a perfect square in the denominator. The first term has a 1 squared. The second term has a 2 squared. The third term has a 3 squared. So the nth term will have an n squared. Yeah, look at us. One more thing I need to do, I need to make it alternate. So should I put negative 1 to the n or negative 1 to the n plus 1? Well, look, the first term is positive. So negative 1 to the n, that's not going to work because that would make the first term negative. So I'm going to need negative 1 to the n plus 1. Or n minus 1, whatever you like. And then, we can write this cuter. We don't need to have this 1 here wasting space. Put this negative 1 to the n plus 1 up there instead. So we have a sub n is negative 1 to the n plus 1 over n squared. Now, finding the formula for a sequence is one of the hardest things for my students to do. And it's just because there is no one set way to do it. You know what I mean? You have to be on the lookout for different patterns. You have to remember arithmetic sequence, geometric sequence, and then this is just like random pattern, perfect squares. Be on the lookout. So if you need more practice, like I said, I do have more videos just on sequences, and they're linked in the description, okay? Here's one last one, little funky, little mean. The sequence is 0, negative 1, 0, 1, 0, negative 1, 0, 1. Okay, so it's alternating, sort of, but then it's also throwing these zeros in between. Is there any function that you've encountered in your math career who does this, that goes 0, then negative 1, then 0, then 1? Cosine, right? The values of cosine at the quadrantial angles, namely like at pi over 2, pi, 3 pi over 2, 2 pi, so on and so forth. Like, I want you to notice this is the same as cosine of pi over 2. Negative 1 is cosine of pi. This is cosine 3 pi over 2. Then now this is cosine 2 pi. Notice I have cosine of, and I keep adding pi over 2. This is 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. This is going to be cosine of 5 pi over 2. So I could say a sub n is cosine of n pi over 2. Okay, and you might say, Professor V, I would have never thought of that. You know, that's okay. Now I showed it to you. Remember, hopefully if you see it again in your lifetime, this moment will come back to you and you'll wow everyone. And just say you thought of it in the moment. Don't say you saw this video, okay? Yeah, have a little fun. Okay, moving on now, let's determine whether these sequences converge or diverge. Now remember, for a sequence, I'm not talking about a series, for a sequence, if the limit as n approaches infinity of a sub n is L, which is finite, right? Some finite number, then we say a sub n converges. If that limit is infinity or negative infinity or doesn't exist, then the sequence diverges. So sequences are very different than series. For testing convergence or divergence of a sequence, all you do is one thing. You take the limit. That's all you do, okay? There's no tests, okay? Good. So here we go. Find the limit of the sequence if it converges. Otherwise, indicate divergence. So what do? It's a sequence. Right away, I just go, oh, I'm going to take the limit as n approaches infinity of a sub n. That's it. Be like a little math robot. That's all you're going to write on your paper. Limit. N goes to infinity. 3 plus 0.1 to the n. Okay, now 0.1, that's 1/10. As n approaches infinity, if I have some number here that's less than 1, and you raise it to something that's getting very, very large, it's going to approach 0, okay? You can take that as a fact. You don't need to prove that or anything. So I can say this right here, 0.1 to the n, is going to go to 0 as n approaches infinity. So the limit of this sequence is going to be 3. Since this limit exists, it's a finite number, then I say the sequence converges, okay? I probably don't need to write converges because they said find the limit if it converges. So by finding the limit, I'm showing it converges. But you know what? When I was a student, I was the ultra paranoid student. I was like, let me not do something that perhaps would cause me to lose points on this exam or assignment or whatnot. So I just wrote everything out, you know. It's good. It's good when you're a student. Be a little worried, yeah. Okay, here's another one. A sub n equals negative 1 to the n times 7 over n. Now this is a little funky because if I try to take the limit as n goes to infinity, we have some problems because of this alternating guy, right? You're like, how do I take the limit as n goes to infinity of negative 1 to the n, because it's going to be bouncing. I don't know. If it's odd, it's going to be negative. If it's even, it's going to be positive. So you don't actually take the limit when you have this alternating term. No, you don't. We use this theorem that hopefully you've seen. I don't expect you to remember it. I just hope you've seen it. The theorem says if the limit as n approaches infinity of the absolute value of a sub n is 0, then the limit as n approaches infinity of a sub n without the absolute value is 0 also. And I've explained this in depth in other videos, but basically, if you make all the terms positive, you make them all positive, and they shrink and approach 0, then even if you left them alone, positive and negative, they're still getting small and approaching 0. That's what that says, okay? So we're going to use this theorem now to find the limit of this sequence, but I'm not going to take the limit directly. I'm going to take the limit of the absolute value of this sequence, exactly. So I'm going to consider the limit as n approaches infinity of the absolute value of negative 1 to the n times 7 over n. And here, this is where the beauty of this theorem comes in. When I take the absolute value of negative 1 to the n, it just makes it positive 1 to the n. And positive 1 to the n is just 1, so I don't even need to write that term anymore. Taking the absolute value just makes it a 1, so it's gone. So now I have the limit as n approaches infinity of absolute value of 7 over n, which is just 7 over n. N's not negative. 7 over n is going to go to 0, right? If n gets very, very large. Oh, perfect. And what did my theorem tell me? If I take the absolute value of the terms and they go to 0, then the original sequence approaches 0. Perfect. So then this tells me the limit as n goes to infinity of the original negative 1 to the n times 7 over n is 0 also. So it converges. How was that? Fun, right? Okay, beautiful. Now let's move on. Slightly different, another alternating sequence. A sub n is negative 1 to the n times 1 minus 7 over n. So let's try the theorem that we just used. It worked so fabulously on that last problem. The absolute value of a sub n would be the absolute value of negative 1 to the n times 1 minus 7 over n. And remember, that's going to make this alternating term disappear because it makes it positive 1. And then nothing in here is negative, so I don't need to keep absolute value bars. I can just write 1 minus 7 over n. So now if I look at the limit as n approaches infinity of 1 minus 7 over n, n's getting large again. Yeah, so 7 over n goes to 0, but this time my limit's 1. Oh, wait a minute. Does the theorem apply? No, look. The limit of the absolute value of the terms has to be 0 in order for us to say that the original sequence approaches 0. So what do we do when it's not 0? Actually, the limit doesn't exist because the even terms, negative 1 to an even number, are all going to be positive and they're going to approach positive 1. And the odd terms, when n is negative, as n gets very large, are going to approach negative 1. This one's bouncing back and forth. So the limit doesn't exist. How do we write up our answer? It depends how picky your instructor is, okay? You could simply write the odd terms approach negative 1 and the even terms of the sequence approach positive 1, which means that the limit as n approaches infinity of a sub n does not exist, so therefore it diverges, okay? Now, that's kind of just like a rough breakdown. If they want you to be like really rigorous about it, then this is how I would write it out. So the odd terms, if we want to represent a term that's odd, you know what, let me start with the even because it's more intuitive. So all of the even terms I can represent with a sub 2n. A sub 2n. Those are the even terms. Think about it. If you take n, which is going to be any natural number, and you double it, then it's even, right? So a sub 2n is some even term of the sequence. A sub 2n is going to be negative 1 to the 2n times 1 minus 7 over 2n, right? I'm just plugging in 2n now here. Well, negative 1 to the 2n, since this is even, it's going to be positive 1. So then this is just 1 minus 7 over 2n. So now the limit as n goes to infinity of 1 minus 7 over 2n, if n gets very, very large, this goes to 0. So this is positive 1. And then we can do the same thing with the odd terms. So how do you represent some general odd term of a sequence? Well, if an even term is 2n, then an odd term is going to be 2n plus 1 or 2n minus 1, right? You start with an even term, and if you add 1 or subtract 1, now you have an odd term. So a sub, let me just do 2n plus 1. That's going to be negative 1 to the 2n plus 1 times 1 minus 7 over 2n plus 1. Now, since I know this is odd, negative 1 to an odd number is going to stay negative. So then I've got negative 1 times 1 minus 7 over 2n plus 1. And I'm just going to leave it like that for a minute. Let me take the limit now as n approaches infinity of this negative 1 times 1 minus 7 over 2n plus 1. Again, this is going to approach 0, but now I have negative 1 times 1, so this limit is negative 1. So notice the even terms approach 1, the odd terms approach negative 1, which tells me that the limit as n approaches infinity of an does not exist. Basically, it's bouncing. Like if I were to, here's 1, here's negative 1, so it's bouncing back and forth like this. The even terms approach 1, odd terms approach negative 1. And later, if you do go on to study higher level math, you'll learn that every convergent sequence, all of the subsequences have to approach the same limit. So you can't extract a subsequence from a sequence. What's a subsequence? Like all the even terms, all the odd terms. You can't have them approaching different limits. If your sequence is convergent, all the subsequences have to converge to that same limit. I hope that makes sense. Okay, enough with that. Let's look at some more, okay? A sub n is 2 minus n plus 3n to the fourth over 5n to the fourth minus 2n cubed plus 2. So again, this is a sequence, not a series. How do I determine if it's convergent or divergent? I take the limit as n goes to infinity every single time. Okay, so how are we going to take this limit? The numerator's approaching infinity, the denominator's approaching infinity. I hope you did not say L'Hopital's rule. No L'Hopital's rule. L'Hopital's rule can only be used on differentiable functions. And a sequence, the terms of a sequence are most certainly not differentiable. If you imagine the graph, they're like this, right? Okay, so they can't be differentiable. They have to be continuous first before they're differentiable. No way, no how. So what do? Again, check with your instructor. If you remember from pre-calc, when the degree of the numerator, degree 4, is equal to the degree of the denominator, degree 4, you can just take the ratio of the coefficients of the leading terms, and that'll give you the limit, right? That's how we found horizontal asymptotes back in the day. But you should probably be more rigorous since you're in calculus now. So what do we do in calculus? Oh, we divide by the highest power of n that's in the denominator. So I'm going to divide everyone by n to the fourth, okay? It just takes a wee bit more time, but it's a lot more intuitive. So limit as n goes to infinity, we're going to have now 2 over n to the fourth minus n over n to the fourth is 1 over n cubed. And then this is plus 3 over, let me distribute now in the denominator. This is 5 minus 2 over n plus 2 over n to the fourth. And then as n gets very, very large, this term will go to 0. So does this guy. So does 2 over n. So does 2 over n to the fourth. And then all I'm left with is 3 over 5, yeah? Okay. So what do I care about 3 over 5? That's my limit. It exists as a finite number. So this sequence converges. Cool. Okay, here's another one. A sub n equals natural log of 9n minus 1 minus natural log 7n minus 2. So again, start off, take the limit as n approaches infinity. We have natural log 9n minus 1 minus natural log 7n minus 2. So as n gets very, very large, this is going to approach infinity. This will too. Hopefully you remember the graph of natural log. As the input gets very, very large, natural log also approaches infinity, right? Here's my rough sketch. Rough, but very lovely little sketch. So then this is approaching infinity. This is approaching infinity, and we are in mild trouble. This is an indeterminate form. Why couldn't this have been a plus? Infinity plus infinity approaches infinity. We'd be done. Obviously, some evil mastermind sat there and made this a minus. Okay, so what do? there's a slew of things, but anytime I see natural logs and I've got this indeterminate form, I go, oh, I'm just going to use my log properties, squish these guys, and write them as one logarithm. And then pretty much problem solved, you know? So this is the limit, n goes to infinity, natural log. I'm going to write it as 9n minus 1 over 7n minus 2. Okay? And then you can just pass the limit through to the argument of the natural log. You can do it in your head, or if you want to write it out, be my guest. So if you want to write out, hey, I'm taking ln, and then I'm going to pass the limit through to the argument, cool. 9n minus 1 over 7n minus 2. And then now it's not a problem. This is going to infinity, bottom's going to infinity, but I'm going to divide everybody by n to the first, highest power from the denominator. Also, if you like to think of it as multiplying by 1 over n instead, that's cool too. You live your best life. Do what feels natural. Just don't forget there's this cute little ln in the front. And then you've got limit, n goes to infinity. This is going to be 9 minus 1 over n over 7 minus 2 over n, right? Love it, love it. N goes to infinity, so 1 over n is going to go to 0. 2 over n is going to go to 0. I'm just left with 9 over 7. That's my limit from all of this. And then I have natural log of that. So then that's natural log 9/7, which exists as a finite number. So this sequence converges also. Look at us, all these convergent sequences. How fancy are we? Okay. Now I'm going to show you another sequence here where we encounter an indeterminate form. Do you know how many indeterminate forms there are? There are 7, just like the deadly sins. If you need a review on indeterminate forms, I have a video for you. I'll link it in the description. Okay, so let's see what's going on here. Let's take the limit, n goes to infinity, 1 plus 8 over n to the n. So as n approaches infinity, 8 over n, that's going to approach 0. So the base here, this is approaching 1 plus 0. It's approaching 1. Raised to the n, raised to the infinity. You guys, this is an indeterminate form. It's not 1. Because the base is not identically equal to 1. It's approaching 1. And I don't know if it's approaching 1 fast enough that this is going to come out to be 1 or possibly something else. I know. This is a sneaky indeterminate form. So what do? This is that scenario where you actually have to use L'Hopital's rule. We're going to take the natural log and move the exponent in the front and then undo the natural log. Do you remember doing this? Yeah. But you're probably like, Professor V, you just told me a couple minutes ago, no L'Hopital's rule on sequences. They're not differentiable. And you are correct. So what do? We weasel our way around it and we go, we're going to let a function of x, which is most certainly going to be differentiable, equal 1 plus 8 over x to the x. And then, so this is y, right, f of x. And now I'm going to consider the natural log of y, which is the natural log of 1 plus 8 over x to the x. And I'm going to proceed and just use x's instead. And then once I get the limit, I'm going to come back and say that's the limit of my sequence. Now you might say this feels like a very silly exercise. Like, why are we just swapping out letters? But it's important because it shows that you understand conceptually when you are allowed to use L'Hopital's rule. Okay, so please don't take this for granted. All right, here's the procedure. Hopefully you remember. If not, like I told you, I got a video for you. Move the exponent to the front. That's the whole point of taking the natural log. Otherwise, this guy's stuck as can be, right? Yep. X times ln 1 plus 8 over x. And then remember, you can only use L'Hopital's rule for indeterminate forms of the type infinity over infinity or 0 over 0. So I got to make a fraction out of this guy. Somebody's going to get moved into a denominator. And you never move the natural log. Yeah, you never move you move the other guy. The other guy moves. So then this is going to become natural log 1 plus 8 over x over 1 over x. That's it. So what do I do with this hot mess? I'm going to take the limit now as x goes to infinity. Natural log 1 plus 8 over x over 1 over x. And then watch this. Look how cool. So x goes to infinity. 8 over x is going to go to 0. ln of 1, yep, that's 0. And then x goes to infinity, 1 over x, that's also going to 0. So now I've finagled things. I no longer have indeterminate form of the type 1 to the infinity. I've got 0 over 0, thanks to this natural log and my slick maneuvering. And I can use L'Hopital's rule. Look at us. You have to tell the people that's what you're doing, though. So you go, I'm using L'Hopital's rule. Watch me go. You do the illegal quotient rule, right? You take the derivative of the numerator separately from the derivative of the denominator. So derivative of ln something is 1 over the something times, I have to do chain rule, derivative of what's inside. Derivative of 1 is 0. Derivative of 8 over x, that's 8x to the negative first. It's going to be negative 8x to the negative second, or negative 8 over x squared. Great. What is the derivative of 1 over x? X to the negative first. It's negative 1 over x squared. Bravo. And then look, negative 1 over x squared cancels out by. This 8 is still there though, right? So I'm going to write it up top here. Don't be scared of the limit. It's going to clean up so cute in just a minute. Limit as x goes to infinity, 8 over 1 plus 8 over x. X goes to infinity, so then 8 over x goes to 0, and this limit is 8. Bravo. That's not the final answer for the limit of my sequence. Because remember, I just showed that the limit of the natural log of y, or the natural log of f of x, is 8. I want the limit of just f of x without the natural log. So how do I get there? Well, the limit as x goes to infinity of just f of x would be e raised to the limit as x goes to infinity of the natural log of f of x, right? You can just pass this e through, they would cancel, and then you would have limit of the original function. So the limit of my original function is e to the 8th. And I don't make my students write this step out every single time. Once they get the limit for the function where you have natural log of whatever it was, I just say, oh, take e and raise it to whatever you had, okay? And then at long last, we can say, well, that means the limit as n approaches infinity of my precious little sequence, 1 plus 8 over n to the n, is also e to the 8th. Okay, I would rewrite that because this here is the limit of the function. You want to address the original problem. Okay, how are you doing? That one was a little spicy, wasn't it? Yeah. Okay, here's another. A sub n equals tan inverse of n over the 7th root of n. Ooh, how do you take the limit as n goes to infinity? I know. Okay, so if we take the limit as n goes to infinity, tan inverse of n over 7th root of n. Do you remember the graph of tan inverse? I hope you do. Tan inverse of x. Oh, it's one of the most famous. It has a horizontal asymptote at pi over 2 and negative pi over 2. Yep. If we're going to positive infinity, hopefully you remember, it looks like tangent who got flipped over on its side. So as n gets very, very large, tan inverse of n is going to approach pi over 2. The 7th root of n, as n gets very, very large, is going to approach infinity. So I just have a constant over infinity. Where's that going? Yes, 0. That's it. Oh, that was pretty harmless. You just had to remember the graph of tan inverse, okay? Good. Good, good. 17, a sub n equals n minus square root n squared minus 2n. Okay, again, we're going to take the limit as n goes to infinity. Let's see. So if n gets very, very large, this is approaching infinity, minus, infinity. There's an indeterminate form. What to do? There's no natural logs here, so I can't use that slick trick that I did previously, but I've been in this scenario before in my life, guys, where I've had infinity minus infinity, and you see how there's a square root? I go, maybe we ought to multiply by the conjugate, top and bottom. So n plus square root n squared minus 2n. That's just the move when you run into this scenario, okay? N plus square root n squared minus 2n. The conjugate, you only change the sign in between. Don't change or don't mess with anything that's under here, okay? And the whole reason we do this is so that we'll have a difference of squares in the numerator, so we won't have any radicals. So limit n goes to infinity. It's going to be n times n, so n squared minus rad n squared minus 2n times rad n squared minus 2n is just n squared minus 2n, no more radical. And then in the denominator, we've got n plus square root n squared minus 2n. Good? Okay, and then I can clean up in the numerator. These n squareds go bye-bye. So we've got limit n approaches infinity, 2n over n plus square root n squared minus 2n. What to do here? Because numerator is going to infinity. This is all going to infinity. No L'Hopital's rule if I can help it, right? Like I know we had to use it in the last one, but it was kind of a pain redefining a function of x. Is there anything else I can do? I could divide by the highest power of n from the denominator, but be careful, it's not n squared because this n squared is under a square root. Technically, it's n to the first, absolute value of n. But since n's going to positive infinity, everything's positive. You don't have to worry about the absolute value. So I'm just going to divide everybody by n. Divide everybody by n. So this is now the limit. N approaches infinity. 2n divided by n is just 2. N divided by n is 1. And then this is where you have to be really careful. When I divide by n, but I put it underneath the square root, it becomes n squared. So really this is n squared over n squared minus 2n over n squared. Because if something is not underneath a radical and then you put it underneath one, for it to be the same, you have to square it. Like say I have the number 5 and then I go, oh, I'm going to put you underneath the square root, but you still want it to represent 5. Well, you got to square it, right? That way it's square root of 25. You see what I'm saying? Okay. So if it's not under a radical and you put it under 1, you got to square it. So this will be 1 minus 2 over n here. 1 minus 2 over n. And then n's going to infinity. So this guy, boop, you go to 0. This is 2 over 1 plus square root of 1. Which is 1. So 2 divided by 2, this limit is 1. And the sequence converges. Ooh, so nice. Okay. Next one. I know we're doing a lot of sequences. Don't worry. I got 100 questions. So we'll talk about series shortly. I just feel like sequences also get neglected. You learn them first and then you don't talk about them for a long time. Assume that the sequence converges and find its limit. Look, you guys, it's another recursive sequence. Back to haunt us. So the first term is -1. Then they say a sub n plus 1 equals the square root of 8 plus 2an. They told me something very important. Assume the sequence converges. That means I can assume that the limit as n approaches infinity of the general term a sub n equals some limit L, and L is a finite number, right? And how do I work with this recursive sequence? Don't let it frighten you. The key is if n's going to infinity and the terms approach L, anytime that subscript gets big, the terms will approach L, meaning the limit as n approaches infinity of a sub n plus 1 equals L also, right? It doesn't really matter if this is n plus 1, n squared. If this is getting very, very large and they told me the sequence converges, then it will approach L. Why am I talking about that? Because we're going to take the limit of the recursively defined sequence. So a sub n plus 1 is the square root of 8 plus 2an, right? I'm going to take the limit as n approaches infinity of both sides. Okay? Don't freak out. You got this. This is fun. So limit as n approaches infinity of a sub n plus 1, that's L. Limit of square root of 8 plus 2an, just pass the limit through. Square root, 8's a constant, plus 2, limit as n goes to infinity of a sub n, where does that go? It's L. It's L. So basically all you do, you take that recursive formula and you replace all the a sub whatevers with L's. Do you see that? A sub n plus 1 became L. A sub n became L. Because they told us I could assume the sequence converges. And then now to find the limit, my job is just solve for L. Pretend you are in a little time machine back in your algebra class and you just have to find L. So let's square both sides. Set it to 0. And then this factors, how lovely, L minus 4, L plus 2. So either the limit is 4 or negative 2. It's the ugliest 2 I've written in my life. Get it together. Okay, so negative 2 doesn't make sense because notice all of the terms are defined to be the square root of 8 plus 2an. It can't come out to be negative because there's no minus sign sitting out here. The first term's negative, yeah. But, I mean, after that, there's no way you're going to get a negative term. So this one makes no sense. Should we tell them we thought about it? I would. I would say, but since a sub n plus 1. This is what I'm talking about. Like, this is the stuff I would write on the test. I'd be like, let me make sure they know what I'm thinking. Right? The limit has to be positive. So L is 4. Good. Good, good. Okay. I think last idea with sequences. Yep. Monotonic and bounded. So if a sequence is monotonic, that means that it doesn't switch from increasing to decreasing. It's always increasing or always decreasing. And there's a difference between when we say monotonic or strictly monotonic, like can it level off or not? We won't talk about all that right now, but basically what you want to do is see if the sequence is always going up or always going down, always getting bigger from one term to the next or always getting smaller. And bounded is another topic that we consider along with it for a very important reason. Bounded means that you can find some number that's an upper bound and another number that's a lower bound for all of the terms on your sequence. And when we put these two ideas together, we can prove that a sequence is convergent. Because if it's bounded, right? And let me graph for you. A picture is worth 1,000 words, so I can say 1,000 words less if you understand this picture. So here's n, here's a sub n. If it's bounded, that means it's trapped between some capital M and some lowercase m, okay? Bounded means all of the terms live in here. Monotonic means it's always increasing or always decreasing. Maybe it levels off, but then it comes back. So if it's always decreasing and it's trapped, then it has to converge, right? It can't like go down to negative infinity. Or if it's increasing and bounded, monotonic, increasing, and bounded, it also has to converge. So that's why these two topics are considered often together. If you can show a sequence is monotonic and that it's bounded, then you can say that it's convergent. Okay? So how do you show that something's monotonic? Couple ways. You can use just straight up definition and compare a sub n plus 1 with a sub n. And if you can show that one is always bigger than the other one, then boom, you can say, hey, every single term that follows is smaller or greater than the one that came before, then you can show it's monotonic. So let's see if that would work here. A sub n plus 1 is 5 times n plus 1 plus 1 over n plus 1 plus 1. So that's 5n plus 6 over n plus 2. Is it obvious that this is bigger or smaller than this, what we started with? No. The numerator got bigger, but so did the denominator. So I can't conclusively say which one's bigger or that it's exclusively one or the other. So when that happens, you can say, all right, let me take the derivative, because I know if a derivative is positive, that tells me a function's increasing. And if a derivative is negative, then the function's decreasing. But again, you can't differentiate the terms of a sequence. So you have to redefine a function. You're going to say, okay, let me let f of x be 5x plus 1 over x plus 1. So then we're going to look at f prime of x now, okay? So f prime of x, yeah, quotient rule time, here we go. Low d high, so denominator times derivative of the numerator, minus high d low over low low. This is going to be 5x plus 5 minus 5x minus 1 over x plus 1 squared. So I'm going to end up with positive 4 over x plus 1 squared, which is always positive, right? As long as x is not negative 1, but we wouldn't substitute in negative 1 for the term of a sequence anyways. So this tells me f of x is increasing. So my sequence a sub n, which is defined as 5n plus 1 over n plus 1, is monotonic, increasing also. Okay, cool. So I got half of the problem answered. Now the second part, is it bounded? So in order to figure out if something is bounded, you need to go find the upper bound and the lower bound. Well, I already got one as a freebie. Which one? So I want to answer the question, is it bounded? Well, think about it. We just showed that a sub n is increasing, right? So that means all of the terms keep getting bigger, bigger, bigger. So a sub 1, the very first term, is a lower bound. And a sub 1 would be 5 plus 1 over 1 plus 1. 6 divided by 2, that's 3. That's the lower bound. Marinate on that for a second. If all of the terms keep getting bigger, then the first term can act as a lower bound. 2 could also be a lower bound. 1 could also be a lower bound. But we're being more precise when, we don't bottom it out more than necessary. When we give the greatest upper bound, we're being more precise. Now, I want to know my sweet little sequence that's increasing. Does it go up and level off? Or does it go up, 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 up forever? So how would I figure that out? How do I know if it levels off eventually or increases forever? I take a limit. So now I'm going to consider the limit as n goes to infinity of 5n plus 1 over n plus 1. And this is how you're always going to figure out if something's bounded. One of the bounds, once you know it's monotonic, either the upper bound, if it's decreasing, or the lower bound, if it's increasing, will be automatically given to you. And then to figure out whether it has the other bound, you would take a limit to infinity. So now I'm going to divide by n, and this is the limit. N approaches infinity, 5 plus 1 over n over 1 plus 1 over n, that's 5. That's the upper bound. So therefore, I could say it's bounded. Okay, and P.S., since AN is monotonic and bounded, it's convergent. I have a whole video just on monotonic and bounded sequences. So if you need to recap, I would hop right over there, okay? It's pretty stellar. But let's do one more, okay? Okay, number 20, same instructions. Determine whether it's monotonic and bounded. Now, if you want, you can do the same thing that we did in the last problem. Define a function of x, take the derivative. I just want to show you something a little different too, in case you want to use the straight up definition. So a sub n plus 1 is 2 minus 3 over n plus 1, right? And can we say whether or not this is strictly larger or smaller than a sub n? We can actually, we really can. So here's the thing. N plus 1, we know that's greater than n, yes? If I take the reciprocal, then the reverse inequality is true. 1 over n plus 1 is going to be smaller than 1 over n. If I multiply by a negative, it flips again. So negative 1 over n plus 1 is greater than negative 1 over n. I'm just trying to manipulate it to look like this guy, okay? So negative 3 over n plus 1 is greater than negative 3 over n if I just multiply through by 3, and the same thing holds if I add a 2. So then I've shown here a sub n plus 1 is greater than a sub n, and that means a sub n is monotonic increasing. Now if you're like, Professor V, that was just way too much finagling with the inequalities. I got you. Another way you could explain it, honestly, my students have done this. 3 over n plus 1 is smaller than 3 over n. So if I'm subtracting something smaller, then obviously this is larger than a sub n. If you hate all of that, that's fine. Hate it. Let's just say we're going to let f of x equal 2 minus 3 over x. Then just take the derivative. What's f prime of x? Well, this is 2 minus 3x to the negative first. So f prime is going to be derivative of 2 is 0. And then this is 3x to the negative second. 3 over x squared. That's always positive, which tells me f is increasing. Therefore, an is increasing. So no matter how you slice or dice it, you should get the same conclusion, obviously, right? Okay, that's done. Now, is it bounded? So if an is increasing, which bound do I automatically have? It's always going up, 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 up. So I automatically have the lower bound. Lower bound is going to be your first term because all the terms keep getting bigger after it. Beautiful. A sub 1 would be 2 minus 3 over 1. So 2 minus 3, negative 1. Okay, is there an upper bound? Remember, how do we check? You always take a limit. Once you've shown something's monotonic, so you have to have already shown it's monotonic, then the first term is either upper bound or lower bound, and then to see if the other one exists, you take a limit. So limit n goes to infinity, 2 minus 3 over n. Well, 3 over n is going to go to 0. So this is 2. So yes, the sequence is bounded between negative 1 and 2. Good? Great. Now you can also most definitely have a sequence that is not monotonic, but it's bounded. I know. We don't have time. I think this video is already, I'm just starting and we're like an hour in for 20 questions. So we got to move on with our lives, but go watch the other video lectures I have on monotonic and bounded sequences. Okay, find the sum of the series. You guys, when you're asked to actually find the sum, that is a huge clue as to what type of series we're dealing with. That is a rare thing. Most of the time, we only determine whether a series converges or diverges. The fact that we can find the sum tells me it is either geometric, telescoping, or a Maclaurin series. Okay? if you're asked to find the sum. Okay, and notice we've moved on from sequences. We have this sigma here. We're summing up from n to infinity the terms 2 over 3 to the n. Well, if they're asking me to find the sum, it's got to be one of these. One of these. It's geometric. Hopefully you can see the common ratio. If not, allow me to rewrite it. So this is the sum. N equals 1 to infinity. 2 times 1 over 3 to the n. And 1 over 3 to the n, I can just rewrite that as 1/3 to the n, yes? 2 times 1/3 to the n. So this guy is definitely geometric. This is r, the common ratio. And as long as absolute value of r is less than 1, it converges, and we can find its sum. And r is 1/3. So the infinite sum, sometimes people write it s, sometimes they put s sub infinity. Doesn't matter. It's always the first term divided by 1 minus r. I don't like to always put a sub 1 because sometimes the first term starts at 0 or somewhere else. So I just write a, but remember it's the first term of the series. This one starts at 1. So the first term, if n is 1, would be 2 times 1/3 or 2/3 over 1 minus r, common ratio, which is 1/3. So this is 2/3 over 2/3, which is 1. Voila, we are done. That was good. That was good. Okay, here's another one. Again, find the sum of the series. It's either geometric, telescoping, or Maclaurin. I mean, it's geometric, right? Can you see what r is, though? It's kind of hidden in there. So a sub n is -1 to the n minus 1 times 9 over 7 to the n. Remember that geometric will have the form a times r to the n, or r to the n minus 1, doesn't matter. I want to get everything that's raised to the n together. So watch how I'm going to break stuff up. I'm going to write this as -1 to the n times -1 to the negative first times 9 over 7 to the n. So now this guy's raised to the n, and so is this. Let me put them together. They're going to be so happy together. So now I have -1/7 to the n. And then -1 to the negative first, that's just -1 times 9. That's -9. Ah, is that helpful? I mean, for me, it's helpful because now I can say, oh, r is -1/7. And absolute value of r is less than 1, so it's going to converge. Perfect. And so now I can find the sum. The sum is going to be the first term over 1 minus r. Now, what's the first term? A sub 1. You can use this version. You can use this version. Doesn't matter. Let me use this one. It's more cleaned up. So -1/7 to the first times -9 is +9 over 7. So that's the first term. That goes up top over 1 minus r is -1/7 here. Okay, so this is 9 over 7 over 7 over 7 plus 1 over 7, 8 over 7. So the sum is 9 over 8. Good? So you just had to kind of rewrite that one so you could identify r more easily. Okay. Find the sum. Here we have n equals 1 to infinity, 1 over 8 to the n minus 1 over 6 to the n. Now be careful here. Separately, each of these can be represented as a geometric series. But remember, you're only allowed to distribute over a sum if we know both the sum of an and the sum of bn converge. Otherwise, this isn't true. Okay, so why am I saying that right now? Because I don't want you to write out something illegal. The math police will come snatch you. You cannot write this is 1 over 8 to the n minus the sum 1 over 6 to the n. You can't do that until you've shown that this is convergent and this is convergent. first. You have to show that first. So don't do this, okay? So you're just gonna say consider the sum n equals 1 to infinity 1 over 8 to the n. That's the same as the sum n equals 1 to infinity 1/8 to the n. This guy's geometric. Absolute value of r, that's 1/8, which is less than 1, so this guy converges. I'll say the sum of this first infinite series is going to be the first term, if n is 1, is 1/8 over 1 minus 1/8. So that's 1/8 over 7/8. So that's 1/7. Okay. Now let's consider separately. This is first consideration. Second consideration, the sum n equals 1 to infinity 1 over 6 to the n. Very similar setup. That's the sum n equals 1 to infinity 1/6 to the n, 1/6 geometric. Same thing, absolute value of r is 1/6, which is less than 1. It converges. So this second sum here, it starts at 1, so 1 over 6 is 1/6 over 1 minus 1/6. So this is 1 over 6 over 5 over 6, which is 1/5. That's my second sum. So now I can say with a clean conscience, all right, both of those were convergent series. So the sum n equals 1 to infinity 1 over 8 to the n minus 1 over 6 to the n. Now I'm allowed to split it up. So you cannot write this step out until you've shown that each of these guys is convergent. Okay? Big deal. Very big deal. Later on, you're going to see how dangerous it is. And then I know this is 1/7 minus, this was 1/5. So that's going to be negative 2 over 35. All right. That's how to appropriately handle that one. Good? Hopefully you guys don't forget that. All right. Let's keep it going. Determine if the series converges or diverges. If the series converges, find its sum. There's that key phrase I told you was very useful. Find its sum. That means it's either geometric, telescoping, or a Maclaurin series. This is most certainly not geometric, nor is it a Maclaurin series. That means it has to be telescoping. Yes. Okay, I have a whole video on that, but we're just going to hop to it. So we have to find the nth partial sum, S sub n. So remember, we switch it up. We introduce a new index of summation. You could do I, you could do K. I'm going to do I. We go I equals 1 to n. This is a partial sum. It stops at n. I'm only adding up the first n terms. And because of that, now I have to change the index here to be I as well. So this is going to be 1 over rad I plus 1 minus 1 over rad I plus 2. And what I want to do is find an expression for S sub n, and then I'll take the limit as n goes to infinity. If I get some finite number, then I know my series is convergent, and that's actually its sum. So telescoping series are cool because everything in the middle cancels out or collapses, much like a telescope. So let's start with I equals 1. If I plug in I equals 1, I'm going to have 1 over rad 2 minus 1 over rad 3. Let me scoot that down. Okay. Plus, now move on, I equals 2. I'd have 1 over rad 3 minus 1 over rad 4 plus, do you need more? Let's keep one more. I equals 3, 1 over rad 4 minus 1 over rad 5 plus, etc. Notice, the telescope is already collapsing on us. 1 over rad 3 cancels, 1 over rad 4 cancels. I'm not going to write any more out, but you could see eventually this would cancel, right? Who's not going to cancel? We have this little survivor out front, 1 over rad 2. I call him a survivor. He didn't cancel. Notice I only have one term surviving, and I'm not shocked by that at all because I plus 1 and I plus 2, how far apart are these two expressions? They're 1 apart, right? From plus 1 to plus 2. So I should have one term survive in the front of this telescoping sum. I'm also going to have one term survive at the end. The number of terms that survive should be the same at the beginning and the end, and it matches how far apart these are. Okay, so the very, very last term would be substituting in n for I. So let me do that one. This would be the last one. So 1 over rad n plus 1 minus 1 over rad n plus 2 plus, who comes before n? N minus 1. Okay, so this would be 1 over radical. This is n minus 1 plus 1, so that's just n, minus 1 over rad n minus 1 plus 2, that's n plus 1. If you want to do another one, you can. I feel good. Like, I know there's one survivor, so I already can tell who it's going to be. We could do another one. Why not? This is rad n minus 1 minus 1 over rad n, dot, dot, dot. Yeah? Okay, so look, who's canceling? And rad n plus 1s. These guys. This will eventually cancel. But here's my survivor. Oh, 1 over rad n plus 2. Look at you go. Okay, so now I have a simplified expression for s sub n. It's just 1 over rad 2 minus 1 over rad n plus 2. All right, so what do we do once we have that? Well, we take the limit as n goes to infinity of s sub n. This is how you always deal with the telescoping sums, okay? And this right here will tell me whether or not my series converges or diverges. Well, as n gets very, very large, 1 over rad 2 is just a constant. 1 over rad n plus 2, that's going to approach 0. So the limit of the partial sums is a finite number. I don't care what it is, just so long as it exists as a finite number. This is actually the sum of my series. And I can say, therefore, it converges. Okay? If this limit comes out to be positive infinity or negative infinity, or if it doesn't exist, then my series diverges. Okay? Very good. Let's see. Here's another. Determine if the series converges or diverges. If the series converges, find its sum. So let's see. Again, they want us to find the sum. So it doesn't look geometric. It's not going to be telescoping because telescoping has to involve subtraction, right? That way when you keep adding the terms, stuff will collapse in the middle. You see how we had subtraction here? That way when I kept listing out multiple terms, we had this cancellation. If there's only one little guy, it can't telescope, and it's not a Maclaurin series. So then if it's not one of the three kinds of series whose sum we can find, then it has to be divergent. And look here, look at the terms. Something very important is going on. A sub n is n over n plus 6. What happens if you take the limit as n approaches infinity of n over n plus 6? If you want to divide by n, top and bottom, right, to take that limit, feel free. So this is the limit. N approaches infinity of 1 over 1 plus 6 over n. So 6 over n is going to go to 0. This limit is 1. You guys, these terms don't go to 0. They approach 1. And we have a test. The test for divergence tells me if the terms of my series don't go to 0, then that means the sum, n equals 1 to infinity, of n over n plus 6 diverges by the test for divergence. Okay, so let me summarize again. You have the sum, what an ugly sigma. You have the sum of an. If the limit as n goes to infinity of an doesn't equal 0, then the sum of an diverges, okay? If the limit as n goes to infinity of an equals 0, no info. So remember, this is called the test for what? The test for divergence. So it can only be used to tell you that your series diverges, and that happens when the terms don't go to 0. If the terms do go to 0, the test is inconclusive. You have to figure out some other way to determine whether the series converges or diverges. Just because the terms go to 0 does not mean anything. It doesn't mean your series converges. It could diverge or it could converge. We don't know. Pick a different test. Just remember, this is called the test for divergence. It can only tell you about divergence, and that happens if the terms don't go to 0. Because basically it's like, if these guys don't even go to 0, there's no way we're going to sit there, add up infinitely many of them, and think it's going to approach a finite number. There's no chance. There's absolutely no chance if these guys don't go to 0 for us to sum them up and it approach a finite number. Okay? Good. I know that one's confusing a lot of the time, but you guys can handle it. Let's look at some more. And then now that you're aware of the test for divergence, hopefully you can kind of like be on the lookout. Yes? Okay. So here we have, again, determine if the series converges or diverges. If the series converges, find its sum. So let's see. They're telling me to find the sum. So if it's going to converge, it has to either be geometric, telescoping, or Maclaurin. It doesn't look geometric. I don't see right off the bat that it's telescoping because I don't see subtraction, but I could find the partial fraction decomposition for a sub n, and perhaps then it will telescope. So let's do that because sometimes that's what you got to do. So we're going to find the partial fraction decomposition for a sub n, which is 2 over n times n plus 3. So that's going to be a over n, because both of those are non-repeated linear factors, plus b over n plus 3. I'm going to multiply everything by n plus 3. And then we've got here 2 equals a times n plus 3 plus bn. Okay, if I substitute n equals negative 3, then I get 2 equals a times 0 plus b times negative 3. So b is negative 2/3. And then if n is 0, I get 2 equals a times 3 plus b times 0. So a is positive 2/3. Okay, very good. So now I can say the sum, n equals 1 to infinity, of 2 over n times n plus 3 is 2/3 over n minus 2/3 over n plus 3. And then hopefully now you can see, oh, I could represent this as a telescoping sum. So S sub n is going to be the sum, I equals 1 to n, and then remember we got to change the n's to i's here, so 2/3 over I minus 2/3 over I plus 3. So let's start listing out the first few terms, starting with I equals 1. So we'll have 2/3 over 1 minus 2/3 over 4, which is going to be 2/3 over 2 over 12, so 1/6. So this is for I equals 1. Plus, now let's move on to I equals 2. 2/3 divided by 2, that's 1/3, minus 2/3 divided by 5, that's 2/15. Nothing's canceling so far. Now let's move on. I equals 3. 2/3 divided by 3, that's 2 over 9, minus 2/3 divided by 6, that's going to give me 1/9. Plus, let's keep it going, I equals 4. 2/3 divided by 4, 2/12, so 1/6. There we go. Minus 2/3 divided by 7, 2 over 21. Do we want another one? Look, finally, you see this guy canceled. Nothing else so far, right? No. I equals 5. Let's do that one. So 2/3 divided by 5, 2/15. Oh, we had that. We had that. Here. Woohoo. Okay. Minus, and then 2/3 divided by 8. That's going to be 2 over 24, 1/12. Okay. But hopefully now you can see, I'm not going to keep going. I'm not. Because this first term canceled with the last term here, just like this first term canceled with the last term here. So the next first term would cancel with exactly this 1/9, eventually. And, oh, let me switch the color. And then, you know, if you just wrote out enough, then these are going to start canceling, so on and so forth. Who doesn't cancel? How many survivors are there? 1, 2, 3. Am I surprised? Not in the least, because look, I plus 3. Those are 3 apart, so I should have 3 survivors here. So I've done enough. Because those are the only ones that matter in the limit, right? Everything else cancels out. I'm trying to find that expression for S sub n. And then I need the ones at the end, because I should have 3 more survivors at the end. So let's do I equals n, right? So we would have, that's the last one, 2/3 over n minus 2/3 over n plus 3. And then before that, we'd have I equals n minus 1. So that would be 2/3 over n minus 1 minus 2/3 over n minus 1 plus 3 is n plus 2. Keep going if you want. How many survivors am I going to have over here? 3, exactly. So I should list out at least 3 terms. You could do more if you are nervous, which I get. So 2/3 over n minus 2 minus 2/3 over n plus 1. Very good. You could do one more. I equals n minus 3. So we'll have 2/3 over n minus 3 minus 2/3 over n. Do you see stuff canceling already? Yes. Okay, so 2/3 over n is gone. And then more would come if I listed more, right? But who's not going to cancel? Who's for sure a survivor? This guy here. Okay, this guy here not canceling out. And this one. The last 3. Just like the first 3 survived, the last 3 survived. And then if I wrote out more terms, then these would all cancel. Okay, these would all cancel. Good. This one's messy, I know. So S sub n is, who survived? 2/3 plus 1/3 plus 2/9 minus 2/3 over n plus 1 minus 2/3 over n plus 2 minus 2/3 over n plus 3. Now what do? We always take the limit of S sub n. I don't feel like rewriting it, you guys. Can I just write lim as n goes to infinity like this? And then I'm just going to do like a little scoot, if you'll allow me. Lim n goes to infinity. These first 3 are just constants, so they don't change. And then, oh, as n goes to infinity, these all go to 0. Okay, so again, this is approaching a finite number. 2/3 plus 1/3 plus 2/9, what's that? That's 11 over 9, which is finite. So this is my sum. This series converges. Okay, now it happens often that this limit will approach infinity or negative infinity. So watch the other video on telescoping sums if you need some more examples like that. Okay, good. Here's one. Determine if the series converges or diverges. If the series converges, find its sum. Oh, again, is it geometric, telescoping, or Maclaurin? Doesn't look like it. So then that tells me it probably diverges. How can I show that? Remember our test for divergence? This is a sub n. It's a constant. It's not changing at all. That means it's just a bunch of rad 7s. I know, how boring. Or how fabulous, right? Because I know for sure the limit as n goes to infinity of a sub n of a constant is itself, which most certainly is not 0. So that tells me then the sum, n equals 0 to infinity of rad 7 diverges by the test for divergence. Yes? And hopefully you could tell, like, if I just sit there and add up a bunch of rad 7s forever, of course that's going to go to infinity. It won't approach some finite number. But that's the formal way to write it all out. Good? Okay, perfect. Let's see, here's another. Determine if the series converges or diverges. If it converges, find its sum. Ooh, okay, I'm going to beat this into your brain until you get it, right? So if it converges, find its sum. Is it geometric, telescoping, or Maclaurin? It looks like it could be telescoping, doesn't it? I think you guys should pause the video, try this one on your own. I sincerely do. Okay, did you pause it? Did you get pi over 4 and it converges? Good. So S sub n is going to be the sum I equals 1 to n tan inverse I plus 1 minus tan inverse of I. Now notice, these are just one apart, so we should have one survivor in the beginning, one survivor at the end. Not as nasty as the other ones. Okay, so I equals 1, let's start with that. So you'd have tan inverse of 2 minus tan inverse of 1 plus, next would be tan inverse of, if I plug in I equals 2, tan inverse of 3 minus tan inverse of 2. Do we need more? Let's do one more. Tan inverse of 4 minus tan inverse of 3 plus blah, blah, blah. So who canceled? Tan inverse of 2, tan inverse of 3, and then tan inverse of 4 will eventually cancel. Here's my one and only survivor, right? Okay, and then the last one, if I plug in I equals n, we're going to have tan inverse of n plus 1 minus tan inverse of n. Before that would be n minus 1, so that's tan inverse of n minus tan inverse n minus 1. Should we do one more? N minus 2 would be tan inverse of n minus 1 minus tan inverse n minus 2. Okay. So I'm expecting only one survivor here as well, right? These are one apart, one survivor. I should only have one survivor at the end. Who's canceling? So tan inverse n minus 1 is gone. Tan inverse, well, if I kept going, just think who would be before. It would be n minus 2, right? So then this guy's going to be gone. You're going to be gone. This tan inverse of n is gone. So here's my one and only survivor. Tan inverse of n plus 1. Oh, wow. So S sub n equals, let me write him first because he's positive. Tan inverse of n plus 1 minus, and you guys should know tan inverse of 1 is pi over 4, right? Yes, don't forget that. Okay, so then now once I have S sub n, I take the limit as n goes to infinity of S sub n. That's the limit, n goes to infinity, tan inverse n plus 1 minus pi over 4. You remember we just graphed tan inverse a hot second ago? So as n gets really, really large, you remember what it approaches? Pi over 2. Remember it had that horizontal asymptote. Perfect. So this is pi over 2 minus pi over 4, which is pi over 4. So that's the sum of my series. Wow, it converges. One cool way to write it, you could write it like this. The sum, n equals 1 to infinity. This, I'm writing the original again. You could say, oh, this equals pi over 4. And then that means it's convergent, obviously, and that's its sum. Pretty cool, huh, guys? Okay, here's another one. Determine if the series converges or diverges. If the series converges, find its sum. Okay, so they said find the sum. That means it's got to be geometric or telescoping or Maclaurin. Ah, it's geometric, isn't it? 1 over rad 6 to the n, that's the same as 1 over rad 6 all raised to the n. So this is geometric. Absolute value of r is absolute value of 1 over rad 6. That's for sure less than 1. So then that tells me it converges. And then the sum is always the first term over 1 minus r. Now the first term in this case, be careful. See how the series starts at 0? So rad 6 to the 0, that's just 1. The first term is actually 1 over 1 minus r, which is 1 over rad 6. Let's multiply everybody by rad 6. That way we don't have that extra fraction in the denominator, okay? So then this becomes rad 6 over rad 6 minus 1. And if we go ahead, let's multiply by the conjugate of the denominator and try to rationalize. It will clean up quite a bit, I know. This is not always fun, but it must be done. So if I distribute this through, this is going to be 6 plus rad 6 over, since I have conjugate pairs in the denominator, that's 6 minus 1, which is 5. Voila. That's a nice final answer right there. We can box it with pride. Okay. Pretty chill. Do you love it? Favorite one of the day? Okay, good. Here we go. Sum n equals 1 to infinity, natural log 4 over n. Okay, again, we have to find the sum. Is it geometric, telescoping, or Maclaurin? Doesn't look like it. So then that probably means it diverges. And right now the only thing you know is test for divergence. So let's see, what's the limit as n goes to infinity of natural log 4 over n? Well, 4 over n is approaching 0. Do you remember the graph of natural log? I drew it for you earlier. Let me put it here again. So natural log goes through 1, 0. And then also, let me put, here's 1, 0. It has vertical asymptote, the y-axis. So it's like this, like this. So as we're approaching 0, and n's positive, so we're approaching 0 from the right, natural log is approaching negative infinity. So this limit is negative infinity, which is most certainly not 0, right? Remember, test for divergence tells us if the terms don't go to 0, then the series diverges. So I can say quickly that means the sum n equals 1 to infinity, ln 4 over n diverges by test for divergence. If you don't like doing the limit this way, let me show you another way. Or you're taking the limit n goes to infinity. I'm going to use my log properties and rewrite this as natural log of 4 minus natural log of n. Okay. And then this way, maybe it's a little easier for you. You go, oh, if n's going to infinity, natural log of n's going to infinity. ln of 4 is just some number minus infinity, that goes to negative infinity. Okay, that's another way of getting that limit. But no matter how you slice or dice it, negative infinity is not 0, so our conclusion is the same. The series diverges by the test for divergence, okay? Beautiful. One more like this, and then we'll move on to another idea. I just want to make sure you guys have this down. Okay, we have the sum n equals 0 to infinity e to the negative 3n. So again, we have to find the sum if it converges. Is it geometric, telescoping, or Maclaurin? Yeah, it's geometric. Look, a sub n is e to the negative 3n, which is the same as 1 over e to the 3n, which I can write as 1 over e cubed to the n. You see that? Ooh, that's fancy. Okay, so then that's my r. Absolute value of r is absolute value of 1 over e cubed, and e is about 2.7. So 1 over that cubed, that's for sure less than 1. So then this guy converges. Let me say it's geometric too. Geometric converges. So the sum is going to be the first term over 1 minus r. So what's the first term? If n is 0, e to the 0 is 1 over 1 minus r is 1 over e cubed. And then don't leave your answer like that. Multiply everybody by e cubed. E cubed. So then we've got e cubed over e cubed minus 1. That's the sum. Cool. Okay, enough of those. Let's move on, but keep in mind, anytime you're asked to find the sum, it's either geometric, telescoping, or Maclaurin. All right, still dealing on the topic of a geometric series, we're asked to find the values of x for which the geometric series converges. So observe we have the sum, n equals 0 to infinity, of x minus 5 over 10 all raised to the n. They're telling us this is a geometric series, and so we should be able to identify what r is, the common ratio. Do you see it? It's right here. Whatever's being raised to the n is r. And now in a geometric series, remember, we require that the absolute value of r be strictly less than 1 in order for the series to converge. So this means that the absolute value of x minus 5 over 10 has to be less than 1, and then this series will converge. And if I solve this inequality and I find x, then I'll be answering the question. I'll find the values of x for which the geometric series converges. So in an absolute value inequality like this, remember, you can drop them now if you want, or you can multiply the 10 over. It doesn't matter which you do first. I'll just drop them now. So we have x minus 5 over 10. Without absolute value, I write that this is less than 1 and greater than negative 1. And then multiplying through by 10, then we have negative 10 is less than x minus 5 is less than positive 10. And then just add 5. So then we have negative 5 less than x less than 15. So as long as x is between negative 5 and 15, then the geometric series will converge. Good? Okay, let's look at some more like this. This time we have the sum n equals 0 to infinity of 6x plus 1 all raised to the n. So can you identify what r is? R is whatever is raised to the n, so in the parentheses right there, r is 6x plus 1, and we require absolute value of that to be strictly less than 1, not equal to. Okay, this is a strict inequality. So then rewriting it without absolute value, I have negative 1 is less than 6x plus 1 is less than 1. And then subtract 1 from everything. So we have negative 2 is less than 6x is less than 0. And then divide by 6. Remember, we're trying to isolate x. So then we have negative 1/3 is less than x is less than 0. So as long as x is between negative 1/3 and 0, the geometric series converges. Okay. All right, now we're asked to find the sum of the geometric series for those x for which the series converges. So they didn't ask us to find the x values that makes it converge, but I'll do that anyways, and then we'll go ahead and find the sum afterward. All right. So let's see if we can identify what r is. It's a little bit hidden in this one. Ooh, look at that. So whatever's being raised to the n is r. Let me see if I can group it all together. This is negative 1 to the n. 3x raised to the 2n. You guys, we can rewrite that as 3x quantity squared raised to the n. Yes? Do you remember your laws of exponents? When you have a power raised to another power, you multiply the exponents. So then now this helps me simplify things. This is negative 1 to the n. Inside I have 9x squared to the n. And then those can get grouped together, negative 1 and 9x squared. And then we just have negative 9x squared to the n. That's a sub n. So here I can clearly see r is negative 9x squared. All right. Now, as long as, remember the absolute value of r, so the absolute value of negative 9x squared is less than 1. And if I take the absolute value of negative 9x squared, that's just the same as absolute value 9x squared is less than 1, right? So as long as this is true, then the sum is going to be a, whatever the first term is, over 1 minus r. So what's the first term of this series? Let's see here. We start at n equals 0. So these raised to the 0 means the first term is 1 over 1 minus r, which is negative 9x squared. So that gives me 1 over 1 plus 9x squared. Good? Now, if you wanted to finish solving this inequality right here and find the values of x that satisfy it, then all you need to do now is divide by 9. So I would say absolute value of x squared is less than 1/9. And then you can go ahead, take the square root here, and the absolute value holds. It is true that the absolute value of x will be less than 1/3. But this is a special case. Normally you can't just go like willy-nilly taking square roots of inequalities and everything's going to hold so beautifully. It does work out though in this scenario because we're basically looking at when is the absolute value of x squared less than 1/9. That's only when the magnitude, right, of whatever I substitute in here is strictly less than 1/3. We can get into more details about it later, but this is fine. Okay. Moving on, let's do a couple more like this. Make sure you have the idea down. So find the values of x for which the geometric series converges. Can you identify what r is? Again, we have to regroup, right? So a sub n is 4 to the n times x to the n. But hopefully this one's pretty straightforward, right? This is 4x to the n. So as long as the absolute value of 4x is less than 1, which means absolute value of x is less than 1/4, then the sum is equal to a over 1 minus r. So what's a? What's the first term? And this is why I don't like to write a sub 1. Some books put the formula that way. Well, the first term isn't a sub 1, it's actually a sub 0. So I just like a generic a nowadays. Maybe I did a sub 1 back in the day, but I've changed my mind since. Okay, so if n is 0, first term is going to be 1, right? Over 1 minus r. I feel like they didn't even ask for that. 1 minus, here's my r, 4x. Yeah, I think I got carried away. I think all they asked for was find the values of x, and I did what it asked for in the last problem. Okay, so here's the values of x. Absolute value of x is less than 1/4. So negative 1/4 is less than x, which is less than 1/4. And then PS, we're so fancy, I gave them the sum too. Why not? Look at us overachieving. Okay, here we go. Now let's practice. Find the sum of the geometric series for those x for which the series converges. So why don't you pause the video, try this one on your own. So you need to figure out what x values the series converges for, and then go ahead and find the sum. Okay, so there's my radius right there. It's x plus 6. So as long as absolute value of x plus 6 is less than 1, which means x plus 6 is between 1 and negative 1, which means as long as x is between negative 7 and negative 5, then the sum equals a over 1 minus r. So what's a? Again, this series starts at 0. So the first term is actually x plus 6 to the 0. That's just 1 over 1 minus x plus 6. So this is 1 over 1 minus x minus 6. So negative 5 minus x. And that's it. Do you want to take the negative out? If I take the negative out, because I'm like, it's looking kind of disgusting, right? Negative x plus 5. And then we could put the negative in the top. Do we like that better? I think so. Looks good. All right. All right, last one like this. Find the sum of the geometric series. And I want you to pause the video, try it on your own, see if you can identify R. Okay, so remember a sub n is -1 to the n. And then 7x to the 2n, do you remember how we rewrote that? 7x squared all raised to the n. So then this is -1 to the n. This is 49x squared to the n. And then you can group everything that's being raised to the n. So then we have -49x squared to the n. So there's my R. R is -49x squared. So as long as absolute value of -49x squared is less than 1, which means absolute value 49x squared is less than 1, divide by 49, absolute value of x squared is less than 1 over 49. So absolute value of x is less than 1/7. Then the sum is going to be the first term. This series starts at 0, so the first term is going to be 1 over 1 minus r, -49x squared. And then just clean up. This is going to be 1 over 1 plus 49x squared. Good? Okay, beautiful. Now, I think we should have geometric series, telescoping, and all that good stuff under control. Moving on, use the integral test to determine whether the series converges. We have the sum n equals 1 to infinity, 9 over the square root of n. So since we're being told to do the integral test, that's exactly what I'm going to do. First thing I need to do is rename f of x and define, or rename a sub n and define it as a function of x. So we're going to say let f of x be 9 over the square root of x. And then in order to apply the integral test, I have to check that 3 conditions are satisfied. First, I have to check if f of x is continuous on the interval that matches where we're summing. So from 1 to infinity. Is f of x continuous on that interval? Well, in order to answer that question, I'm going to consider what's the domain of f of x. So notice here, f of x, I have a square root in the denominator. I can't take square roots of negatives, and also that x can't be 0. So the domain of f is all values from 0 to infinity. And I know since f is a combination of, a rational function, a radical function, we have a theorem in Calc 1 that tells us it's continuous on its domain. So its domain is from 0 to infinity. I'm interested in continuity on 1 to infinity. This is the subset, right, of 0 to infinity. So we're good. So of course f is going to be continuous on the subset from 1 to infinity. Done. Second thing I need to check, is f of x positive on 1 to infinity? Again, 1 to infinity, I'm coming up with that because I'm looking what we're summing over. Yeah, if I take the square root of anything, it's not going to come out to be negative. So we're good to go. Usually this condition, you just look at it and put a check. Just think about it for a second. And then the third thing I have to check is f decreasing on the interval from 1 to infinity. So it might be obvious to you because notice only the denominator changes as x changes. And if x gets larger, f of x gets smaller. If that makes you too nervous to just say by inspection, or if your instructor wants something really rigorous, you could just take a quick little derivative. So we know f of x is 9x to the -1/2. F prime of x would be -9/2 x to the -3/2. Good. So this is -9 over 2x to the 3/2. This denominator is always positive. I'm taking the square root of something and then cubing it. And then the numerator is negative. So negative divided by a positive, this first derivative is always negative. So if the first derivative is negative, then of course the function is decreasing on 1 to infinity. So now I can say, all right, we're in the clear. I can apply the integral test, all right? So the first thing you do is you say, let's consider the integral from 1 to infinity of that function, 9 over square root of x dx. Okay, first things first, anytime you have an improper integral, you have to rewrite and replace this upper limit with a dummy variable. Usually we use t, and then we take the limit as t goes to infinity instead. And then you keep all the rest the same. I'm going to actually rewrite this already as 9x to the negative 1/2 dx because I want to get ready to take the antiderivative. Okay? Good. And then from here, hopefully it's nice and straightforward. So keep writing lim until you actually evaluate the limit at the very end. I'm going to add 1 to the exponent, divide by the new exponent, and notice I just brought the 9 down. Nothing happens to that 9. So if I add 1, I'm going to have x to the 1/2. Dividing by 1/2 is multiplying by 2 over 1. And then I evaluate this from 1 to t. All right? So then we have now the limit. T goes to infinity, 18. T to the, or let me, yeah, you can plug it in. We're ready. This is going to be square root of t minus square root of 1. Good? Okay. So now as t approaches infinity, square root of t, that's approaching infinity. This is just a constant. So what's going on here? This is getting very, very large. Times 18, it's still getting very, very large. So this limit is infinity, which tells me that the integral, my improper integral, diverges. And if my improper integral diverges, then that tells me that the sum, n equals 1 to infinity of 9 over the square root of n, also diverges by the integral test. Okay, good. So just as a recap, make sure that you don't forget to check that these 3 conditions are satisfied. That tells us that it's okay to use the integral test. And I know you might be saying, well, they told me to, though, in the directions. I would still check, okay? Unless your instructor tells you otherwise. Still check always. Most of the time, you're not told what test to use anyhow, so then you would absolutely need to check that it's appropriate. Okay, here's another one. Integral test again. Here we go. So we're going to let f of x be 5x over x squared plus 2. Now we have to check, is f continuous on 1 to infinity? Well, look at f of x. It's a rational function, but this denominator is never 0. So the domain of f is all real numbers, which means f is continuous on all real numbers. So yes, it's continuous on the interval from 1 to infinity. 2, is f positive on 1 to infinity? Well, look, the denominator is always positive, and then I'm only looking at the interval from 1 to infinity. So if I'm only plugging in values of x that are from 1 to infinity, of course that's positive. Yes. And then the third thing is f decreasing. Ooh. This time I definitely need to take the derivative to take a closer look at what's going on. It's not obvious. So let's see. F prime of x, quotient rule time. So we've got low d high minus high d low over low low. This is going to give me 5x squared plus 10 minus 10x squared over x squared plus 2 squared. So let's see now, this is going to be negative 5x squared plus 10 over x squared plus 2 squared. Well, the denominator, I can tell, that's always positive, right? The numerator, if x is 1, the numerator is going to be positive. Positive over positive is positive. That means f prime is positive. F is not decreasing if x is 1. That's problematic. What about if x is 2? Negative 5 times 4, 20. Negative 20 plus 10. Yeah, then it's negative. If x is 3, if x is 4. Honestly, forever onward, we're good. The only problem is that if x is 1, then the derivative is positive. So I can say this derivative is less than 0 if x is greater than or equal to 2. So no, it's not decreasing on 1 to infinity. It's decreasing on 2 to infinity. And you know what? That's good enough for our purposes. That's eventually decreasing, and we'll take it. That's fine. So what should you do from here? Does that mean you need to come in and switch this to a 2 now and switch our integral instead of going from 1 to infinity? Should we go from 2 to infinity? If you really want, you can, okay? You don't have to, because here's the thing. If this integral converges, it will still converge whether or not I include 1 or I don't include 1. And if this integral is going to diverge, it will still diverge, whether or not I start at 1 or I start at 2. It makes no difference. So if your instructor is particular, do whatever they say. It's not such a huge deal. As long as we can say it's eventually decreasing, we're happy. Even honestly, if it's at x greater than 100, as long as you can pinpoint finitely many places where it's not, and then from there on, it's decreasing, that's honestly good enough, okay? So you live your best life. If you want to start at 2, go for it. I'm just going to leave it. 1 is such a nice number, you know. So let's consider integral from 1 to infinity 5x over x squared plus 2 dx. First thing you got to do, quick as a bunny, rewrite it as a limit. Limit t goes to infinity, integral 1 to t 5x over x squared plus 2 dx. Okay, now this integral, we can't just, boom, take the antiderivative. We have to do a cute little u sub. So I'm going to let u be the denominator. Let u be x squared plus 2. Then du is 2x dx. I don't quite have that. Don't worry about the 5, just the x dx. So that means 1/2 du is x dx. So now I can rewrite this integral all in terms of u. We've got limit t goes to infinity 5 times, instead of x dx, I have 1/2 du over u. And then notice I didn't write limits of integration because we have to change them as well since we did a u sub. So u is x squared plus 2. These limits belong to x, so I'm going to plug them in for x. So u of 1 squared plus 2, that's 3. So my new lower limit's 3. And then u of t would be t squared plus 2. How are we doing? Good? Okay. 5/2 is nothing more than a constant, so we can take it outside the integral. So this is limit t goes to infinity 5/2 3 2 t squared plus 2 1 over u du. You know the antiderivative of 1 over u? Oh, good for you. Yes. ln, absolute value of u. So limit t goes to infinity 5/2 times natural log absolute value of u evaluated from 3 to t squared plus 2. So then we have limit t goes to infinity 5/2 times natural log absolute value t squared plus 2. That's already positive, so I'll just put parentheses, minus natural log of 3. And then, okay, t is going to infinity. So if this goes to infinity, the natural log of all of that is also going to go to infinity. I have infinity minus some number. So this is all still going to infinity. times 5/2, that's positive. So this is all going to infinity, which tells me the integral diverges. Very good. Okay, so then what can we conclude from there about our infinite series? It also diverges. So the sum n equals 1 to infinity, 5n over n squared plus 2 also diverges by the integral test. How was that? All right, good. I got, I think, one more integral test for you, and then we'll move on to the other tests. Okay, this is for sure the spiciest integral that we've done so far. So we have the sum n equals 1 to infinity, 3 over e to the n minus 1. So we're going to go ahead, let f of x be 3 over e to the x minus 1. And let's check that all three conditions are satisfied before we use the integral test. So first, I want to see, is f continuous on the interval from 1 to infinity? Well, what's the domain of f of x? The only problem I would have is if the denominator is 0. This is 0 if e to the x is 1. That happens if x is 0. So my domain is all x's such that x can't be 0. But we're good to go because 1 to infinity doesn't include 0. So perfect, check. Next, I want to see, is f positive on the interval from 1 to infinity? Well, yeah, look, the numerator's positive. E to the first, that's 2.7 minus 1, that's positive. And then for everything larger than that, we're good. Just put a little check, we thought about it. And then lastly, is f decreasing? So again, this one you can kind of just look at it and see it will satisfy that condition because this is just a constant. As x gets larger, the denominator gets larger, so the whole thing's getting smaller. If you want to really check and know through and through, then you can take a derivative. I'm just going to ask you to remember this is 3 times e to the x minus 1 to the negative first. We don't need to do quotient rule because there's no variables in the numerator. So then if we take f prime of x, bring that negative 1 down front, and this is going to be negative 3 times e to the x minus 1 to the negative second, good. And then by the chain rule, I got to multiply by the derivative of what's in here, which is e to the x. So then cleaning this up, this is negative 3 e to the x over e to the x minus 1 squared. This denominator is always positive. E to the x is always positive. And then here's a negative constant. So negative times positive divided by a positive. This is for sure less than 0, which means f is decreasing. Perfect. So now it's okay to use the integral test. We can hop to it. Let's consider now the integral from 1 to infinity of 3 over e to the x minus 1 dx. Whew. So let's rewrite this. First things first, limit t goes to infinity, integral 1 to t, 3 over e to the x minus 1 dx. Now what would you do here? How do you take this antiderivative? No, you don't get to just ln the denominator. I hope you weren't thinking that. So we're going to do a u sub, but we have to kind of be a little clever with it. I'm going to let u equal e to the x. And then du is e to the x dx. And you might say, Professor V, things are not looking good. I don't see that anywhere. And you're right. So what I'm going to do is rewrite this as du over e to the x is dx. And remember, e to the x is just u. So actually, I can replace dx with du over u. And that'll fix things. So now we still have 3 over, remember, e to the x is u minus 1, and then dx gets replaced with du over u. Okay, hopefully you've seen this little maneuver before. Now, what are my new limits? These limits belong to x. So let me see what they are in terms of u. U of 1 is e to the first, so that's just e. And then upper limit, u of t is e to the t. That's my new upper limit. All right. Did we make life better? We did, don't worry. So this is limit, t goes to infinity, e to the t, and then this is 3 over, maybe if I write it like this, you'll feel better, u times u minus 1 du, right? That's the same thing. And then now, yeah, let's go ahead, let's find the partial fraction decomposition for this guy. Oh, okay, everything's coming full circle, right? Partial fraction time, okay. So 3 over u times u minus 1. Those are both linear non-repeated factors. So we've got a over u plus b over u minus 1. Multiply through by the LCD, then I'm going to have 3 equals a times u minus 1 plus b times u. If I let u equal 1, then I have 3 equals a times 0 plus b, so b is 3. And then if I let u equal 0, then 3 equals negative a, so a is negative 3. And then we should be good to go. So now we have limit t goes to infinity, integral from e to the t. A is negative 3, so negative 3 over u plus b is 3 over u minus 1 du. Let me add a page. We're getting squished here. Okay. And then we know those antiderivatives. Make sure you keep writing lim every step of the way. So antiderivative of negative 3 over u is going to be negative 3 natural log absolute value of u plus, and then this antiderivative is going to be 3 natural log absolute value u minus 1. All evaluated from e to the t. Okay, to evaluate this limit, I'm going to clean up and make my life a little bit easier. I'm going to factor out this 3, and then I'm also going to use my property of logarithms to combine these into one natural log. So watch, I have limit t goes to infinity, take the 3 out, and then I have natural log absolute value. The positive natural log's argument goes in the numerator, u minus 1 over u, like this. Evaluated from e to the t. And then I can clean this up and write it as u over u minus 1 over u. And that'll be nicer when I'm evaluating at the limits of integration. I'm just trying to clean as I go. That way, in the end, I don't have this nasty limit to evaluate. So this is ln absolute value 1 minus 1 over u. You see that? I don't know if you guys cook, maybe not that much yet, but I'm fanatical about cleaning as I go. That way there's not this disaster at the end. So think of math the same way as you go. If there's things you can combine and simplify, take care of it. Because see, I'm going to have such a cute little limit in just a second. All right, we're almost there. Limit t goes to infinity 3 times. This is going to be natural log absolute value 1 minus 1 over e to the t minus natural log absolute value 1 minus 1 over e. Okay, we good? Perfect. As t goes to infinity, 1 over e to the t, that's going to go to 0. Then this is just natural log of 1, so this whole thing is just going to go to 0. And then what's going on with the rest of it? This is all just some constant. 3 times negative natural log 1 minus 1 over e. And I don't need absolute value. 1 over e is smaller than 1, so it's not negative. So this is negative 3 ln 1 minus 1 over e. I don't really care what this number is. All I care is that it's finite, right? All I care that the limit exists. It's a finite number, which tells me that the integral converges. Ooh, okay. So then that tells me at long last that that sum, where was he? I forgot what he was. It's been so long. The sum n equals 1 to infinity of 3 over e to the n minus 1 also converges by the integral test. All right, how was that? Now, sadly, had this been a plus one, we could have been done in less than 1 minute, because then we could have applied the comparison test. Yes. So, what is the comparison test? It's pretty cool. The comparison test. First of all, make sure you only apply it when you have two series whose terms are positive, okay? If the terms of one series are always less than or equal to the terms of the other series, and the bigger series converges, then our smaller series, the sum of those terms, the sum of an, also converges, okay? The direction of the inequality is very important because the bigger series converging forces the smaller series to converge. And that's why it's also important that we have positive terms. If we didn't require that, this could diverge if the terms could go down to negative infinity. But since we're forcing all the terms to not be negative, then a larger series converges, forces a smaller one to converge as well. Now, here's where things get tricky. If an is less than or equal to bn, and the larger series diverges, then we have no info, because the sum of an could converge or diverge. Okay, so it's very important that you have the correct inequality there. Now, other way to apply the direct comparison test. If an is greater than or equal to, make sure you have that equals to bn for all n, and the sum of bn diverges, then the sum of an also diverges. So basically, in this case, if the smaller series diverges, then the larger series also has to diverge. This should make sense because if we're requiring, again, that the terms not be negative, the smaller series diverging forces the series whose terms are larger to also diverge. But again, be careful, because if an is greater than or equal to bn and the sum of bn converges, then again, no info. Okay, the sum of an could converge or diverge. And I don't stress about which one's an, which one's bn. Who cares? Just remember, the larger series converging forces the smaller one to converge. The smaller series diverging forces the larger one to diverge. And that's the only way direct comparison works. Now, what if you can't show the correct inequality? What do? If the comparison test does not apply, a lot of the times instead you can just use the limit comparison test. And this is more of a fan favorite, I have to say. My students don't like the comparison half as much as they like the comparison. So suppose the sum of an and sum of bn are series with positive terms. We know that. If you take the limit as n goes to infinity of the ratio of the terms, an over bn, and you get some constant c, and it's positive. So it can't be 0, it has to be positive, and it has to be a constant, so it can't be infinity. Then both series converge or diverge. This is so beautiful. I like to say both series behave the same. They're basically twinsies. So whatever you compared it to, if you get some non-zero constant, you know your series does the same thing as the other guy. And who do we usually compare our series to? We compare them to p-series and geometric series. Those are the two most popular choices. So when you do this test, you compare with p-series and geometric most of the time. Once in a while it might be something else, but this is like the most popular. And then if c ends up being 0 or infinity, either you chose the wrong sum to compare it to, okay, or you need to pick a different test. or choose a different test. So it's a U problem. Does that make sense? So don't sit there and go, oh, I got C is 0. That means nothing. That means you need to go back and fix something. All right. All right. So let's see how to apply it. And I'm not going to force you to do one or the other. Use the comparison test or limit comparison test to determine if the series converges or diverges. So here we have the sum n equals 2 to infinity, 1 over square root of n minus 1. So first thing I do is I think if I'm going to compare it to somebody, it's either going to be a p-series or geometric series most of this time. This is definitely reminding me of p-series. It's reminding me of the sum. Let me just start n equals 2 also to infinity of 1 over square root of n. That's a p-series, right? P is 1/2, which is less than 1, and it diverges. Now, I know most of the time p-series starts at 1. It doesn't matter if it starts at 2. It could start at 100. It's still going to be a divergent p-series. So can I use direct comparison or do I have to do limit comparison? Let's think back. This guy diverges. If I can show that the terms here, 1 over rad n minus 1, are bigger than the terms of this divergent series, then my series must diverge also. So can I show that 1 over square root of n minus 1 is greater than or equal to 1 over square root of n? I think so. It's pretty straightforward. Square root of n minus 1, we know that's less than or equal to square root of n, right? And you might say, Professor V, why are you writing or equal? It's strictly less than. That's true, but I'm not wrong if I put or equal to. It's more like a little safety buffer, okay? And therefore, if I take the reciprocals, 1 over square root of n minus 1, that's going to be larger than 1 over square root of n. Okay, so I just justified that this sum here diverges because it's a p-series. And if the terms of my series are larger, then I can say for sure, I'm summing up a bunch of stuff that's bigger than that divergent p-series over there. So certainly this also diverges by comparison. I just did direct comparison. Sometimes it's called direct comparison. Okay. I know, sometimes this one can be a lot. Let's look at another example. Here we have the sum, n equals 1 to infinity, 5 over n squared plus 4n plus 3. So this is also reminding me of a p-series. Which p-series though? 5 over n squared, 5 over 4n, which one? You always look at the highest power because that one's running the show. So this is giving me vibes of 5 over n squared. And that's not exactly p-series, but we know we can take a constant outside of a sum and it doesn't affect whether it converges or diverges. So this is a constant multiple of a p-series. P is equal to 2, which is greater than 1. So we know this series converges right here. So if this series converges, here are its terms. Can I show that these are smaller than the terms of this convergent series? If so, then I can just use direct comparison. Well, yeah, because look, all I have is more stuff in the denominator. More stuff in the denominator means a bigger denominator. It means you're dividing by something bigger. For sure, that's less than or equal to 5 over n squared. And since I know this, the sum of 5 over n squared converges, then that means the sum, n equals 1 to infinity of 5 over n squared plus 4n plus 3 also converges by comparison. So what would you need to include for like a full credit answer? The inequality, and then justification as to why you know the sum of 5 over n squared converges. So you would need to say it's a p-series, identify p. I would even include that constant multiple and say it explicitly, okay? State the test, rewrite the original series you were given. That's how I would do it. Okay, here we go. Now let's see a scenario where direct comparison doesn't work. Okay, I've already spilled the beans. Sorry, spoiler alert, but it happens. Here we have the sum n equals 2 to infinity, 1 over square root of n plus 1. This is so super similar to the one we did 2 problems ago, but there was a minus in the denominator instead. Okay, who is this reminding you of? If you're going to compare it to somebody, yeah, it's still reminding me of that same p series, n equals 2 to infinity, 1 over square root of n. This guy is p series, p is 2, no, 1/2, which is less than 1, so it diverges. Now, in order for me to use direct comparison, I need to show, can I show that 1 over square root of n plus 1 is greater than or equal to 1 over square root of n? Because this series diverges, I need to show that my terms are greater than or equal to the terms of this divergent series. Can I show that? No, I can't this time. Because square root of n plus 1 is actually bigger than square root of n, so 1 over square root of n plus 1 is a wee bit smaller than 1 over square root of n. Oh no. So does that mean that this series, it's going to converge? Certainly not. No. This plus 1 really isn't doing a whole lot. It's just I can't use direct comparison test anymore. So instead, I'm going to use limit comparison. So when you can't show the inequality that you need, you use limit comparison instead. All right. And you're going to compare it with, yes, 1 over rad n. So we're going to look at the limit as n goes to infinity, and I take the ratio of the terms of those two series. So 1 over rad n plus 1 over who I'm comparing it to, 1 over rad n. Okay, so this is limit comparison. Now we have to take a limit. Okay, so this is limit, n goes to infinity. The 1 over rad n in the denominator is going to flip up to the numerator here. So now I have rad n over rad n plus 1. Divide by highest power of n in the denominator, which is rad n. So that's the same as multiplying by 1 over rad n. Beautiful. So then now we have the limit, n goes to infinity. This is going to be 1 over 1 plus 1 over rad n. All right, so if n gets very, very large, 1 over rad n, that's going to 0. And then we have 1 over 1, so this limit is 1. Which test did I just use? Limit comparison. When I take the limit, all I care is that it's finite and it's not 0. 1 is finite, yep, and it's not 0. So what does that tell me? It tells me my series is twinsies with the one I compared it to. Who did I compare it to? This divergent p series right here. So that means my series diverges also. So the conclusion doesn't depend on what this number is, right? As long as it's finite and non-zero, the conclusion, whether it converges or diverges, depends on what you compared it to. This tells you they behave the same. So this tells me that the sum n equals 2 to infinity of 1 over square root of n plus 1 also diverges by the limit comparison test. It's at that point in the video where I am abbreviating like a madwoman. Oh, yes. Okay, I hope that was fun for you. Was it fun? I'm loving it. I'm having a grand old time. Let's do some more. This limit comparison test is nice because you don't have to stress about the direction of the inequality, you know? Use comparison or limit comparison. All right, cool. We have the sum n equals 1 to infinity, 4 rad n over 10n to the 3/2 minus 7n plus 2. So when it's looking like a hot mess express and you're like, I don't even know where to begin. What would I even think about comparing it to? Just look at the highest power of n in the numerator and the highest power of n in the denominator, okay? In the numerator, we've got rad n, that's n to the 1/2. I don't really care about the 4. You can use it, you cannot use it. I feel like less is more in this case. In the denominator, please don't get overwhelmed. What is the highest power of n? It's n to the 3/2. You got it. Does this simplify? Yes, this simplifies to 1 over n. What do I know about 1 over n? Not much. This is nothing. We're trying to do limit comparison test. I need to compare it to another series. The sum n equals 1 to infinity of 1 over n. What do I know about that series? Oh, this is the harmonic series. It's a special P series. It's so special it has its own name. And we know the harmonic series diverges. Oh. So then I have a feeling like this guy's going to diverge as well. Oh, yeah. Because basically all this extra stuff is just fluff. What's running the show are the highest power terms. And so I'm pretty sure this guy's growing or shrinking, however you want to think about it, just like the harmonic series. Very close to it. Maybe off by a constant multiple, but not much else. I'm not really in the mood to fuss with an inequality. If I can show this is bigger than the harmonic series, then I can just do direct comparison. But if you're like, I just don't want to deal, then let's use a limit comparison test and not have to stress. So we're going to take the limit as n goes to infinity of the terms of our series, 4 rad n, over 10n to the 3 halves minus 7n plus 2 over 1 over n. Okay. This will flip up. So I'm going to multiply by n. So then I have 4n to the 3 halves in the top, right? So limit n goes to infinity, 4n to the 3 halves over 10n to the 3 halves minus 7n plus 2. To take this limit, let's divide by n to the 3 halves. Highest power of n from the denominator. And then now we've got the limit, n goes to infinity. This is 4 over 10 minus 7 over n to the 1 half plus 2 over n to the 3 halves. And then n's getting large. So this will go to 0, this will go to 0, and I'm left with 4 over 10, which reduces to 2/5. What do I care about 2/5? Just that it's finite and not 0. So then that tells me my series is twins, or it behaves the same as whoever I compared it to. I compared it to a divergent harmonic series. So my series diverges also. So this means the sum, n equals 1 to infinity. I would rewrite it. I would rewrite the original, yep. Remember I told you I was like that paranoid student. Also diverges by the limit comparison test. Okay, how do you feel? Let's see if you can do one on your own. I mean, you don't have to, but I think it's good. Now's the time for you to shine. Take the reins, see if you can do it. We've got the sum n equals 1 to infinity, n squared plus n plus 3 over 2n to the 4th minus 9n plus 7. Yeah, so who are you going to compare it to? Remember, no panic attacks. Just look, what's the highest power of n in the numerator? N squared. In the denominator, n to the 4th. You can or cannot include the 2. It will make no difference. This simplifies to 1 over n squared. Don't forget, 1 over n squared is meaningless. The sum, however, n equals 1 to infinity of 1 over n squared. Now that's a P series. P is 2, which is greater than 1, and it converges. I mean, this isn't meaningless. It's just this represents the terms of a sequence, perhaps, not a series. So make sure you don't forget to write this part out. Don't just write 1 over n squared converges. That's not true. 1 over n squared, what the heck? That's not even a series. You have to write out a series. That's my point. Okay, so what do you think? Do you think this will probably converge too? Because remember, these guys are running the show. This is just a bunch of extra fluff. So it's probably growing or shrinking, just like this P series here. Now, if I'm going to use direct comparison, I have to show that the terms here are smaller than 1 over n squared. I don't think we can do that. So now's a great time to use a limit comparison test. I'm just saying, I'm not going to fuss with any inequalities. I'm just going to take a limit like a boss. So limit n goes to infinity, n squared plus n plus 3 over 2n to the fourth minus 9n plus 7 over 1 over n squared. Okay, cool. Then dividing by 1 over n squared is the same as multiplying by n squared, so I'm going to distribute it through the numerator. This is limit, n goes to infinity, n to the fourth plus n cubed plus 3n squared over 2n to the fourth minus 9n plus 7. And then to take this limit, I would divide everybody by n to the fourth. And then let's see, we've got now limit, n goes to infinity, 1 plus 1 over n plus 3 over n squared, and then 2 minus 9 over n cubed plus 7 over n to the fourth. You're going to 0. You're going to 0. You too. And you. So I'm just left with 1/2. What do I care about 1/2? That it's finite and not 0. So that tells me my series is twinsies, behaves the same as this convergent P series. So then my sum, n equals 1 to infinity of n squared plus n plus 3 over 2n to the fourth minus 9n plus 7 also converges by the limit comparison test. Beautiful. Ugh, I'm so proud of you guys. Okay, remember I also said you'll do limit comparison test with geometric on occasion. Yes, not exclusively P series. So let's try one more and then we'll move on. So here we have the sum, n equals 1 to infinity, 4 to the n plus 1 over 3 to the n minus 2. Again, like, don't freak out. Just look at who's running the show in the numerator and the denominator. So 4 to the n plus 1, that's the same as 4 to the n times 4 to the first. So basically 4 to the n is the exciting part, this constant 4. Yeah. And then 3 to the n minus 2. The minus 2 we don't really care so much about. So really what's going on is we've got 4 to the n over 3 to the n, which is 4/3 to the n. Well, what do I know about the sum, n equals 1 to infinity of 4/3 to the n? This is a geometric series. Yep. R is 4/3. Ooh, that's greater than 1. So this series diverges. So I can do limit comparison test, take the limit of these terms over 4/3 to the n. If I were to just do direct comparison, I would need to show that these terms are larger than 4/3 to the n. Can I do that? Actually, I think I can. So then I don't even have to mess with taking a limit. This might be fast. Because look, 4 to the n over 3 to the n minus 2, isn't that greater than or equal to 4 to the n over 3 to the n? Take a second, think about it. I just made the denominator smaller here, yeah, by subtracting 2, which makes this whole thing bigger. Yeah. And then also, let me make this even bigger. Let me multiply by another 4. 4 to the n times 4 over 3 to the n minus 2 is greater than or equal to 4 to the n over 3 to the n. So then now I've shown 4 to the n plus 1 over 3 to the n minus 2 is greater than or equal to 4/3 to the n. So then I'm done. I showed the inequality that I needed. N equals 1 to infinity, 4 to the n plus 1 over 3 to the n minus 2 also diverges, not by limit comparison, but just by direct comparison. Okay, this one I know is trickier to grasp. If you need more practice, I have extra videos on this, so go check it out. There's more examples. But let's get into some alternating series now, yeah? Yeah, sounds good to me. So determine the convergence or divergence of the alternating series. Here we have the sum, n equals 1 to infinity of -1 to the n over 5n cubed plus 8. All right, so let's see. For alternating series, usually most people call b sub n, whatever this original term was without the alternating part. So b sub n is going to be 1 over 5n cubed plus 8. So if you want to think about it this way, a sub n is your -1 to the n times b sub n. Although this is sometimes -1 to the n plus 1 or n minus 1. So just ignore the alternating part. The rest of it is b sub n. So when we do the alternating series test, we need to check two things. First, we need to check, is b sub n decreasing? So you can do this again if you need to redefine it as a function of x and take the derivative. In this case, we don't have to go that extreme. I can just say b sub n plus 1 would be 1 over 5 times n plus 1 cubed plus 8. And for sure, I just made the denominator bigger than what it was. So for sure, that's less than or equal to 1 over 5n cubed plus 8, which is b sub n. So since I just showed that b sub n plus 1 is less than or equal to b sub n, that means b sub n is decreasing. That's literally the definition of decreasing. So we are good. And then the second thing I want to check is what's the limit as n goes to infinity of 1 over 5n cubed plus 8. So as n goes to infinity, this denominator is getting super big. Numerator's a constant, so this is going to 0. And that's precisely the second condition that needs to be satisfied. The limit as n goes to infinity of b sub n needs to be 0. If both those conditions are satisfied, then I can say that my original sum, n equals 1 to infinity, -1 to the n, over 5n cubed plus 8 converges by the alternating series test. Now, if either of those conditions is not satisfied, then you need to go back and pick a different test. Usually it does mean, yes, that your series will diverge, but as far as my classes are concerned, I still make them show it using an appropriate test. Most often it's test for divergence. Just check with your instructor. So when AST fails, what do they want you to do? I say use an appropriate test to justify your conclusion. Okay. Let's try a couple more. Good stuff here, people. So we have the sum n equals 1 to infinity, -1 to the n, natural log of 6n plus 3 over 6n plus 2. So can you identify what b sub n is? B sub n is natural log 6n plus 3 over 6n plus 2. So the first thing I want to do is see if bn is decreasing. And you guys, it's not going to be obvious. B sub n plus 1 is ln 6 times n plus 1 plus 3 over 6 times n plus 1 plus 2. I mean, I don't know. This got bigger, this got bigger. Who's to say? Who's to say? So I feel like this is the perfect time we should just say, let's let f of x be natural log 6x plus 3 over 6x plus 2, and then just take the derivative and see if it's always negative, okay? Don't take the derivative just yet. We have this beautiful natural log, so let's use our properties and split it into 2. This is natural log 6x plus 3 minus natural log 6x plus 2. Then you don't have to do nasty, nasty quotient rule, right? Because we have chain rule situation going on. So f prime of x, derivative of ln something is 1 over the something, and then I do have to multiply by the derivative of what's inside, which is 6. Minus, similarly, this is going to be 6 over 6x plus 2. And maybe here you can already tell it's negative. Can you? Like this denominator is bigger, they have the same numerator. So this guy's smaller than this guy. So I can already tell, yep, it's negative. If that felt just too crazed for you, I understand. So what else could you do if it wasn't so obvious? Just get a common denominator. So you'd have 6 times 6x plus 2 minus 6 times 6x plus 3 over 6x plus 3 times 6x plus 2. And then if I distribute in the numerator, those 36x's will cancel out. I have 12 minus 18, so negative 6 over 6x plus 3 times 6x plus 2. Now, what can I say about this derivative? Well, remember, x isn't really going to be any real number. X is only going to take on the values that n takes on, 1 to infinity. So if we're only plugging in numbers from 1 to infinity, for sure that denominator is positive. This numerator's negative. Negative divided by positive, that's negative. For all or for every x that's greater than or equal to 1. So we're good. That means f is decreasing on 1 to infinity, so b sub n is decreasing. Perfect. All right, second condition. Now let's check what's the limit as n approaches infinity of b sub n, of natural log 6n plus 3 over 6n plus 2. Well, again, you can pass this limit inside. So we have natural log of the limit as n goes to infinity, 6n plus 3 over 6n plus 2. And then not taking any shortcuts, I'm just going to divide everybody by n to the first. That's the highest power of n from the denominator. So I've got natural log of the limit. N goes to infinity. This is going to be 6 plus 3 over n over 6 plus 2 over n. And then these guys both go to 0. 6 over 6, that's 1. So I'm left with natural log of 1, which is 0. Perfect. Remember, the limit of bn needs to go to 0. So both conditions are satisfied. Fabulous. This means the sum, n equals 1 to infinity, negative 1 to the n, natural log. You know, they put brackets when they wrote it. So I will too. Did you see that? I'll do the same thing. 6n plus 3 over 6n plus 2 converges by the alternating series test. I always am more happy when it converges than when it diverges. Are you the same? Yeah, I don't know. Okay. 49. You guys are almost at the halfway point. Look at us go. So if you try to do AST, it will fail both conditions. Do you see that? Bn is 3n to the 8th plus 1 over 4n cubed plus 6. If you already can see one of the conditions is going to fail, do that one first. Like, you don't have to check them in order. Like, it's really easy for me to see the limit as n goes to infinity of bn. If I divide everybody by n cubed, you're going to have n to the 5th up top. This goes to infinity. Do you want me to show it? Let me show it. Limit n goes to infinity. If I divide by n cubed, I'd have 3n to the 5th plus 1 over n cubed. You only divide by the highest power of the variable from the denominator, okay? From the denominator. So you wouldn't divide by n to the 8th. No, no. These go to 0. Infinity divided by 4 is still infinity. So that's definitely not going to satisfy condition 2. Remember, the terms need to go to 0. So it fails AST. Yes, this series diverges, but how should we show it? I'm going to use the test for divergence. Because one thing I want you to know, it's an alternating series, yes? But the terms are getting very, very large. And since it's alternating, that means all of the odd terms, which are going to be negative, the odd terms are going to approach negative infinity, and the even terms are going to approach positive infinity. We showed this at the very beginning when we looked at an alternating sequence, actually, in this video, and we did something similar. So in fact, if you want to say the limit of n approaching infinity of -1 to the n, 3n to the 8th plus 1 over 4n cubed plus 6 does not exist because the odd terms approach -infinity and the even terms approach +infinity. And if the limit of the terms doesn't exist, then most certainly the limit is not 0, right? That means the limit as n goes to infinity of a sub n is not 0. So the sum, n equals 1 to infinity, -1 to the n, times 3n to the 8th plus 1 over 4n cubed plus 6 diverges by the test for divergence. That's it. That is it. Okay. If you want to be really rigorous and write it out, you can. Look back to how I did it in the sequence that we did. Oh God, it was like at the beginning of the video, where you would look at a sub 2n, a sub 2n plus 1, and then you could show the limit of one of them is +infinity, the limit of the other is -infinity. Okay? Good, good. I'm going to do a couple more, finish up alternating series, and I feel like we should just do this in 2 parts because, I mean, holy smokes. What am I going to put out, a 7-hour video? I don't know. So now one more thing, alternating series estimation theorem. So if you have some alternating series and it satisfies the 2 conditions of the AST, meaning you know it's a convergent alternating series, then we have this fabulous theorem that tells us about the magnitude of the error or the remainder if we only sum up the first n terms. So S is the true sum, S sub n is the partial sum from adding up the first n terms. This is your error. That error is always less than or equal to b sub n plus 1. So if you add up the first 4 terms, the error from that is always going to be less than or equal to b sub 5. If you add up the first 100 terms, the error from that partial sum to the true sum is always less than or equal to b sub 101. And this image kind of helps you understand why that is. Here's the true sum. Here's our alternating series, and here's the first partial sum. The error from that first partial sum to the true sum is smaller than b sub 2. So look at the error. Here's the first partial sum. Here's the true sum. This is the error. This is the error. And then here's b sub 2. In magnitude, this is less than this, right? And this works because when you have an alternating series, because the signs are changing, these partial sums keep shrinking and approaching the true sum, and that error right here, this difference is always going to be less than whatever b sub n plus 1 is going to be. And this works if you keep going. And so you get a very nice error bound here. Say I looked at the second partial sum. Here's the error, second partial sum from the true sum, right? That's error. Well, our estimation theorem tells us that that is smaller than whatever b sub 3 is. Oh yeah, look at that. Okay, and so on and so forth. Okay, so here we go. Pretty straightforward examples. Estimate the magnitude of the error. So they don't care if it's positive or negative, just how much, involved in using the sum of the first 4 terms. So we're summing up the first 4 terms. N is 4. To approximate the sum of the entire series. So we're not summing up infinitely many, we're just summing up 4. How off are we? So the remainder or the error from summing up the first 4 terms by the alternating series estimation theorem is less than or equal to b sub n plus 1 or b sub 5. So literally just find b sub 5 and that's your answer. Can you identify what b sub n is? It's all the stuff without the alternating part. There it is, hidden. B sub n is 0.5 to the n over n. So b sub 5 is 0.5 to the 5th over 5, which is 0.00625. If you want, we could just write 6.25 times 10 to the -3rd. That is not a lot of error. I mean, I guess it depends what, a lot is to you, but. Okay, let's try another one. Same thing, we're only summing up the first 4 terms. So the magnitude of the error for the sum of the first 4 terms is less than or equal to b sub 5. What's b sub n? Can you tell? Yes, it's 1 over 6 to the n. Good, good, good. So b sub 5 is 1 over 6 to the 5th. So that's 0.00012886. And then this we can write in scientific notation, 1.29 times 10 to the negative 4th. I don't know, check with your instructor how they want the final answer, right? Do they care? Sig figs? Usually not for math. All right, last one. Determine how many terms should be used to estimate the sum of the entire series with an error of less than 0.001. Okay. So we want the error from summing up the first n terms to be less than or equal to 0.001. Okay. So I know that error is always less than or equal to b sub n plus 1. That better be less than or equal to 0.001. What's b sub n? Can you even tell? Yeah, it's this part here. B sub n is 1 over 6n squared plus 1. So b sub n plus 1 would be 1 over 6 times n plus 1 squared plus 1. I need that to be less than or equal to 0.001. Okay. If I take the reciprocal of both sides, that means 6 times n plus 1 squared plus 1 has to be greater than or equal to reciprocal of 0.001, 1 over 0.001, that's 1,000. Yes? Good. Which means 6 times n plus 1 squared has to be greater than or equal to 999. Oh, okay. Which means n plus 1 squared has to be greater than or equal to 999 divided by 6, 166.5. Take the square root, that means n plus 1 has to be greater than or equal to 12.9. Okay, and then n has to be greater than or equal to 11.9. So if n has to be greater than or equal to 11.9, we can't choose something that's not an integer. So we need to choose n to be 12. Good? And then as long as we sum up the first 12 terms, so then the error from summing up the first 12 terms is going to be less than or equal to b sub n plus 1, b sub 13, which is 1 over 6 times 13 squared plus 1, which is like 0.000985, blah, 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 which is just under the error that we needed. If you did any less than that, then the error would go up and we wouldn't satisfy the inequality. Okay? I think I'm going to stop there. That's part 1. We made it through 52 questions. I have 53 through 100 ready, but let me hydrate and get my energy back so I can be nice and peppy and explain things patiently, thoroughly, and in an excited fashion to keep you engaged. Next up is the ratio test. Ratio test, root test, absolute and conditional convergence. Then I promise we're going to do radius of convergence, interval of convergence, power series, Taylor, Maclaurin, finding limits using Maclaurin series, all sorts of good stuff. I know, I feel like the end is really where it's going to ramp up. So turn on your notifications. I've put myself in some sort of lockdown right now. I skipped yoga today. Can you believe it? I didn't go to hot yoga just so I could record and get this out for you guys in time for finals. I hope to have it out ASAP, but make sure you're subscribed and you have that notifications bell going so you know when it uploads. Don't forget to give this video a thumbs up. Please leave me a comment down below. Tell me your favorite problem. When are your finals? Soon? Are you watching just for fun? Even better, personal enrichment. We love that. Also follow me on Instagram, TikTok. I'll show you behind the scenes, a little bit of my life and the craziness that encapsulates it, but it's all good stuff. I love you guys so much. Thank you for your support. I will be back sooner than later. Oh yes, I promise. Ta-ta.